Hello there and welcome to Science for Sleep, where curiosity takes its time, science wears its softest slippers, and we wander together through the gentle edges of knowledge. Tonight, we're looking outward, far outward, to something that has arrived here from an almost unimaginable distance. It's an object with a name that sounds a little like a code, a little like a treasure map, and a little like the kind of thing you might overhear in a quiet observatory at 3 a.m. It's called 3-Eye Atlas, and it isn't from here. Not from our solar system, not from any planet we know, not even from the vast cloud of comets that hovers at the sun's outer reach. It has come from beyond. Not beyond in the dramatic sense of science fiction, with glowing engines and mysterious pilots, but beyond in the real, silent way of deep space, drifting through the interstellar void for longer than human civilization has existed, and maybe longer than Earth has had forests. You might think of the solar system as a small town, familiar and bounded with the sun in the middle and the planets as its streets. Most of what passes through here belongs to the town in one way or another, asteroids and comets looping around on long orbits, dust swirling in from collisions, the occasional meteoroid dropping by. But every so often, something comes along that is clearly not from here. You can tell by its path, you can tell by its speed, you can tell by the way it doesn't seem to care about the sun's gravity any more than a passerby cares about a streetlight in a city they're just passing through. That's what 3-Eye Atlas is. It's a passerby. A visitor who, for a brief moment in the entire history of the solar system, has happened to wander close enough for us to notice. Before we wander too far into its story, I wonder where you are as you're listening. Are you lying in bed, in the deep part of the night, with your room lit only by a faint glow from a screen? Are you somewhere with the sound of rain in the background? Or maybe you can hear the faint hum of a refrigerator in another room. If you could look out your window right now and see through all the city lights or clouds, you'd be looking into the same sky 3-Eye Atlas has crossed. No matter where you are, the space above your head is part of the same vast backdrop it came from. If you find this quiet journey as comforting as it is curious, you might like to keep this little corner of calm company again. A like or a subscribe is always welcome here, not as a demand, but as a way of keeping the lights on for more nights like this, when we can slow down and follow a story all the way into the dark. Now, about that story. The first thing to know about 3-Eye Atlas is that it's not a comet like the ones we've seen dozens of times before. At least, not entirely. And it's not an asteroid in the familiar sense either. Astronomers have had to look closely to decide what category it even belongs in. But the second thing to know is that the numbers in its name are part of a kind of quiet code used to keep track of discoveries like this. The 3-Eye means it's the third interstellar object ever confirmed. The I is for interstellar, of course, and that puts it in the rarest of categories. The Atlas part is the name of the survey system that found it, and that's where the story of how it came to our attention begins. It was April 2024 when the Atlas system spotted something that didn't quite match the pattern of the usual suspects in the sky. Atlas, short for Asteroid Terrestrial Impact Last Alert System, is a network of telescopes designed to catch objects that might be heading our way, particularly the kind you'd want to know about if they were going to get uncomfortably close. These telescopes quietly scan the night sky from Hawaii and other locations, snapping image after image, comparing them to earlier ones, looking for movement. Most of what they find are asteroids from the main belt or comets swinging in from the far edges of the solar system. Every so often, something a little more unusual comes into view. What made this one stand out was its orbit, or more precisely, the fact that it didn't have one in the usual sense. It wasn't bound to the sun in an ellipse. Instead, it was on a path that could only be described as open-ended, a hyperbola. That's the mathematical shape you get when an object passes by with enough speed that the sun's gravity can't hold on to it. Instead of looping back, it comes in once and keeps going, heading back out into interstellar space, never to return. That was the first sign that this wasn't a local. Astronomers have gotten better at spotting these outsiders in recent years, partly because our surveys are sharper and more complete than ever before, and partly because we're now aware that they're out there. For most of history, objects like this would have been invisible to us. They would have passed through in silence, undetected, maybe even relatively close to Earth, without anyone knowing. It was only in 2017 that the first confirmed interstellar visitor was spotted, Oumuamua, and then in 2019 came 2I Borisov. To have a third arrive within just a few years is remarkable, though whether that's because they're more common than we thought or because we're finally looking carefully enough is still an open question. You can imagine the scene in an observatory when something like this turns up. At first, it's just a moving point of light in a field of stars, faint and ordinary looking. The motion tells you it's close enough to be part of the solar system, but when you plot that motion over a few nights, you see it doesn't fit the patterns you expect. The calculations tell you it's not coming from the outer planets or the Oort cloud. It's coming from farther away than that. And that's when you realise you might be looking at a traveller from beyond the sun's reach. If you think about the scale of the distances involved, the quietness of its arrival is striking. 3I Atlas has been moving through space for perhaps millions of years, far from any star, cold enough that its surface temperature might have been just a few dozen degrees above absolute zero. It would have been invisible to any human eye, drifting in a place where the nearest light is so faint it might as well be the dark between breaths. And then, by chance, its path happened to line up with the thin disk of planets and dust that make up our solar system. It entered from somewhere in the constellation Serpens, or at least that's the part of the sky we can trace it back toward. That doesn't necessarily mean it came from a star in that direction. Interstellar paths can be bent by encounters with other stars or massive objects, but it gives a kind of rough return address on its galactic postcard. As it approached, the sun's heat would have begun to wake it up if it were icy, as comets usually are. That heating can release gases trapped for eons, making a faint coma or tail. In the case of 3I Atlas, there were hints of such activity, enough that many astronomers lean toward calling it a comet, though it doesn't quite behave like the ones we're used to. Whatever it's made of, it has held onto those materials since before it left its home system, which means studying them can tell us something about the conditions around another star, possibly long before Earth was even here. Thinking about that is a little like holding a stone in your hand that you know came from another continent, carried across the ocean by unknown hands and dropped in your path. Except in this case, the ocean is the space between stars, and the stone has been travelling on its own for most of its existence. That's the quiet, understated wonder of 3I Atlas. It's a small thing, hard to see, fleeting in its visit, but it's proof that the space between stars isn't empty of connection. Objects can and do cross that space, carrying with them tiny clues about where they began. When astronomers saw it, they knew time was short. These objects move fast, dozens of kilometers per second, and their visit to the inner solar system is measured in months, not years. Observatories around the world began tracking it, each trying to catch it while it was still bright enough for detailed measurements. Because the next time it passes this close to a star might be millions of years from now, and it won't be our star. Every scrap of data we can get now is all we'll ever have. And that's where we find ourselves, following the faint path of a visitor who won't stay long, learning what we can before it slips back into the dark between suns. From here, the details begin to build into a fuller picture, not just of what it is, but how we know, and what its journey tells us about the galaxy around us. It helps to start with the basics before we follow its path too far. That name, 3I Atlas, is both a label and a clue. The 3 tells you that this is only the third confirmed time astronomers have seen something from outside our solar system pass through. The I is short for interstellar, which in astronomical terms means its orbit cannot be explained by anything that began under the sun's gravitational influence. It came from beyond the region where our planets, asteroids and comets formed. The Atlas part is the name of the project that found it, a reminder that behind the mathematics and orbital diagrams, there are teams of people running surveys night after night, looking for faint moving points of light among the stars. Most of what Atlas finds are objects that are entirely at home here. They may be newly discovered, but they belong to familiar families, asteroids from the belt between Mars and Jupiter, comets from the far-off Oort cloud, or the occasional near-Earth object that demands more immediate attention. But every so often, something moves in a way that sets it apart. When the telescope images of 3I Atlas were compared across successive nights, its apparent motion didn't match any known object, and when its orbit was calculated, the numbers came back with an unmistakable result. The eccentricity, the measure of how far an orbit is from being a circle, was greater than 1. That is the mathematical fingerprint of a hyperbolic path. An eccentricity of 1 means a perfect parabola, barely enough speed to escape the sun forever. Anything greater means the object is not just escaping, it's passing through with speed to spare, and no amount of solar gravity can pull it back. For astronomers, that's like seeing a footprint in the snow that leads in from outside your yard and heads straight through the gate on the other side. Whatever left it is not from here, and it won't be staying. That realization is what elevates 3I Atlas from another faint smudge in the nightly images to something of special importance. You could study 1,000 comets from our own Oort cloud and learn about the outskirts of the solar system, but studying one interstellar object offers a glimpse into somewhere else entirely, another star's outskirts, another system's history. Of course, calling it somewhere else is easier than being specific. Tracing an interstellar object back to its point of origin is difficult, often impossible, because the galaxy is not a still photograph. Stars move, and their motion changes the gravitational landscape an object travels through. Over the millions of years 3 Atlas has likely been drifting. It may have passed close to other stars, been nudged slightly off its original trajectory, and had its speed altered by encounters we'll never know about. That means when astronomers try to project its path backward, the uncertainty grows quickly. You can say it came from a general region of the sky, roughly towards Serpens in this case, but identifying a specific home star is beyond our reach with current data. What we can say is that its speed relative to the Sun is far greater than the local escape velocity. When it was first observed, 3I Atlas was moving at about 26 km per second relative to the Sun, and that's after climbing out of the Sun's gravity well. If you roll the clock back to before it approached our solar system, its speed in interstellar space would have been even higher, perhaps over 30 km per second. That's faster than most comets in our own system, and it fits with the idea that it's been moving freely under the influence of the galaxy's general gravitational field rather than bound to any one star. Size is harder to pin down from Earth. A telescope can measure how bright an object appears, but brightness depends on both size and reflectivity. A small object with a bright, icy surface can appear the same as a larger object covered in darker material. For 3I Atlas, estimates put its diameter somewhere in the range of a few dozen to perhaps a few hundred meters. It's small enough that even the largest telescopes see it as a point of light, but large enough to survive countless micrometeoroid impacts and the stresses of long travel between stars. One of the intriguing parts of its discovery was the possibility that it was showing cometary activity. When icy materials are warmed by the sun, they sublimate, turn directly from solid to gas, and can create a diffuse cloud called a coma, sometimes with a tail. The data from Atlas and follow-up observations suggested that 3I Atlas might have a faint coma, though nothing as spectacular as the bright tails we see on some comets. If that coma is real, it means the object has preserved volatile ices for the entire time since it left its home system. Those ices would be chemical time capsules, locked away since they formed. That's valuable because the chemistry of ices can tell you a great deal about the environment where they condensed. Ratios of certain isotopes, the presence or absence of particular molecules, these are fingerprints of the temperature, composition and radiation conditions around the object's original star. Studying those fingerprints is like receiving a sample return mission from a star we've never visited. In this case, the sample is fleeting and untouchable, but its light carries the information all the same. Spectrographs can split that light into its component wavelengths, revealing absorption features that match specific substances. Even a faint spectrum can be enough to start building a chemical profile. This is where the rare nature of interstellar objects becomes clear. With a bound comet from our own system, we have many chances to observe it. If we miss one pass, it will be back in decades or centuries. With 3i Atlas, the window is one time only. That makes every clear night, every instrument pointed its way, and every measurement worth treasuring. The data taken now will be all we ever have to understand it. That urgency is one of the unspoken pressures in professional astronomy. The sky is vast, but some opportunities happen once in a human lifetime, or once in all of human history. Beyond its chemical and orbital properties, there's the question of how 3i Atlas came to be on this path in the first place. The most likely scenario is that it formed in the outer reaches of another planetary system, perhaps in a belt of icy bodies like our Kuiper belt, or in a more distant cloud of comets. Over time, gravitational interactions, perhaps with giant planets or a passing star, could have nudged it inward toward its own star, where an encounter with a massive planet slingshotted it outward at escape velocity. Once free of its star, it would wander through the galaxy indefinitely, unless captured or destroyed along the way. Our solar system is simply a waypoint on that endless journey, one of countless gravitational fields it will pass through before fading into the background again. It's tempting to imagine a more dramatic story, that it was ejected violently during the early chaos of its system's formation, or that it carries fragments of a world shattered by collision. Those are possible too, because the early life of planetary systems is full of violent reshuffling. The truth is, 3i Atlas could be an utterly ordinary representative of interstellar debris, or it could be an unusually preserved relic. Without a sample in hand, we have to let its light and motion be our guides. There's also the matter of naming conventions, which to an outsider might seem bureaucratic, but they're part of the precision needed in tracking and communicating about objects like this. The 3i designation will never change, even if further observations refine our understanding of its nature. That fixed label makes sure that anyone in the future looking at the archives will know exactly which discovery it refers to. The Atlas tag honours the survey that found it, in the same way that 2i Borisov bears the name of its discoverer, and 1i Oumuamua carries a Hawaiian name given in recognition of where it was spotted. In astronomy, naming is both practical and ceremonial. It tells you who found the object and preserves a piece of its history. The more we examine 3i Atlas, the more it fits into a growing picture of what the galaxy is like beyond our own star. For a long time, the idea of interstellar objects was more theoretical than observational. We knew they must exist. Planetary systems can't hold on to everything they form, and ejected bodies should wander freely, but we hadn't seen any. Now, with 3 confirmed examples, we're beginning to see them as a small but real part of the solar system's traffic. They are reminders that we are not isolated. Material is constantly exchanged between stars, even if on timescales so long that it escapes ordinary notice. All of this brings us to a kind of quiet realization. 3i Atlas is not special in the sense of being unique. There are likely countless others like it, crossing the galaxy in every direction. What makes it special to us is timing and awareness. It happened to pass close enough for our instruments to catch it, and we happened to be watching with the right tools to recognize it for what it is. For all we know, hundreds of similar objects have passed through the solar system in the past, invisible to human eyes, and hundreds more will do so in the future. But for now, we have this one, and the chance to learn from it while it's here. Names in astronomy often sound like a strange combination of letters and numbers, and 3 Atlas is no exception. At first glance it might seem impersonal, a dry label chosen for convenience, but each part of it is a signpost pointing toward the object's place in a much larger story. There's a practical reason for this string of characters, and behind that reason is a long tradition that has grown as the sky has been catalogued. When astronomers talk about naming something, They're not thinking about what looks good on a book cover or a headline. They're thinking about clarity, permanence, and the ability to share information without confusion, no matter when or where it's read. The first piece, the 3, is more significant than it looks. It doesn't refer to size or brightness or order of discovery in a single night. It means that this is only the 3rd object ever confirmed to have come from beyond the solar system. The first was given the label 1I Oumuamua, the second 2I Borisov, and now we have this one. That number alone is enough to tell astronomers how rare such discoveries are. It's not that only 3 of these have ever passed near the Sun. There may have been thousands, millions, over the lifetime of the planets, but these are the only 3 that have been spotted, tracked, and confirmed with the precision needed to prove their interstellar origin. That 3 puts it in a very small and special catalogue, one that didn't exist before 2017. The I in the middle is for interstellar. It's the official way of marking that an object's orbit isn't closed around the Sun. This is not just a comet with an unusually long path or an asteroid knocked into an odd trajectory. It's something on a one-time pass. Once it's gone, the Sun's gravity won't be able to pull it back. That designation, I, was new when Oumuamua was named. Before that, no official category existed for these travellers, because no one had seen one closely enough to make it necessary. Now, with 3 confirmed, the I has become a small but important part of the astronomical naming system. The final part of the name, Atlas, tells you who first saw it and announced its existence. In this case, it refers to the Asteroid Terrestrial Impact Last Alert System, a set of wide-field survey telescopes designed to detect objects that might come near Earth. The name of the survey becomes part of the object's name, not as a matter of vanity, but as a record. If you go back into the data years from now, that tag will tell you exactly which set of instruments first picked it up. For other objects, that part of the name might be the surname of a human discoverer, a combination of names in cases of independent discoveries, or the acronym of a survey project. Sometimes, as with Oumuamua, there's a second, unofficial name given by the discoverers or the local community, something more memorable to the general public. Oumuamua, for example, is a Hawaiian word meaning scout, or messenger from afar arriving first, chosen because the discovery was made by a telescope in Hawaii. Borisov simply carries the name of the amateur astronomer who first spotted it, Gennady Borisov. As of now, 3I Atlas doesn't have a widely adopted name beyond its designation, though it's possible that one could be suggested, either by the discoverers or by public contest. Such a name wouldn't replace the official designation in scientific records, but it might make its way into popular science articles or outreach materials. These names are more than labels. They're part of the story of how we interact with the universe. Long before telescopes, bright comets were given names that reflected the culture and era of their observers. Some were named for the year they appeared, others for the constellation they seemed to emerge from, and still others for events they coincided with. In the modern era, where many discoveries happen through automated surveys and software, the process has become more systematic. Every letter and number serves a purpose. The year of discovery, the order in which it was found, the type of object, all of these can be encoded in the official name. For an interstellar object, the process is slightly different, because the I takes the place of the usual C for comet or A for asteroid. That change signals to everyone who reads it that this object doesn't fit the normal pattern. When the Atlas system first picked up the moving point of light that would become 3I Atlas, the designation it received was a temporary one, reflecting the date and sequence of discovery. These temporary names are like placeholders, useful for tracking observations in the early days, but replaced by the permanent designation once enough data has been collected. The confirmation of its interstellar origin is what triggered the assignment of the 3I label, making it part of that rare catalogue. By the time that happened, the initial observations had already been sent to the Minor Planet Center, the clearinghouse for such data, where orbital calculations confirmed it couldn't be from the solar system. For people outside astronomy, the use of strings like Three-Eye Atlas instead of something lyrical might seem disappointing. Why not name it after a mythical voyager, or a long-lost city, or a bird that migrates between continents? The answer comes down to communication and record-keeping. When thousands of discoveries are made every year, many with similar characteristics, precise and standardized naming prevents confusion. A poetic name can inspire curiosity, but an exact designation makes sure scientists know they're talking about the same thing in every paper, every database, and every observation log. That doesn't mean these names can't carry their own kind of quiet romance. There's a certain weight to knowing that 3i means it's part of a group so small you could memorize the entire list in a moment. There's history in seeing Atlas there, a reminder that this discovery came not from a single person peering through a telescope on a chilly night, but from an automated network designed to watch the whole sky with patient precision. That network has its own story, a development born of the need to detect near-Earth asteroids, repurposed here to find something far more distant in origin. Without it, this interstellar traveller might have passed by unnoticed. If we look ahead, the catalogue of interstellar objects will almost certainly grow. New survey systems are coming online, like the Vera C. Rubin Observatory with its legacy survey of space and time, which will scan the sky in unprecedented detail. Each new detection will get its own number and tag, each will be entered into the same careful registry, and each will join the lineage started by Oumuamua in 2017. At some point, we may no longer think of 3i as the newest member of a tiny family, but as one of the early ones, part of the first handful we ever knew. That perspective will take decades to arrive, but astronomy is comfortable with long waits. In the meantime, the name serves its immediate purpose, to anchor this object in our records, to link every observation and every piece of analysis back to a single identifier. If you come across a spectrum labelled 3i Atlas in a database years from now, you'll know exactly which object it refers to. If a spacecraft proposal is written with that name in its title, you'll know what the mission planners are aiming for. If a future researcher compares its properties to those of 7i or 12i, the naming system will make the lineage clear. There's also a human side to naming, even when the names are coded. For the people who work on surveys like Atlas, seeing their project's name attached to a rare discovery is a moment of recognition. It's a sign that their work has contributed something lasting to the field, something that will be cited and discussed far beyond the moment of discovery. The Atlas project was built for planetary defense, to find potentially hazardous objects in time to act. But along the way, it has also found something that expands our view of the galaxy itself. Having that reflected in the object's name is a subtle acknowledgement of how interconnected different goals in astronomy can be. All of these layers, the numbering, the letter for interstellar, the survey name, form a compact record of 3 Atlas's place in the history of observation. It's not meant to be evocative in the way a folk name might be, but it holds information that will matter long after the object has faded from sight. In the same way that a star's catalogue number tells you its coordinates and brightness without ever describing its colour or its place in a constellation, the designation for an interstellar object is a map folded into a few characters. You have to unfold it to see the bigger picture. Once you do, the next natural question is how those characters came to be attached in the first place. Not just in terms of naming rules, but in the exact sequence of moments when the object first appeared in the data, how it was recognised as unusual, and how that recognition spread from one set of observers to another. That story begins not in a flash of dramatic discovery, but in the routine scanning of the sky, where most of what's seen is ordinary, until one faint dot stands out just enough to change its place in the catalogue forever. The idea of 3i Atlas being the third of its kind only makes full sense when we look back at the first two. Until 2017, interstellar objects belonged mostly to theory. Astronomers knew they should exist. The logic was straightforward. Planetary systems form in messy ways, with countless small bodies left over after planets take shape. Many of those leftovers get flung into far-off orbits, or even thrown completely free of their home star's gravity. Once that happens, they drift through the galaxy indefinitely, crossing the empty light years between stars. Given enough time, some of them should wander through our solar system. It was a reasonable prediction. But a prediction is only that, until you have evidence, and for centuries there was none we could point to. That changed in October of 2017, when an automated survey picked up a moving speck in the constellation Lyra. At first, it looked like a typical asteroid discovery. Small, faint, on an odd trajectory but nothing unheard of. The initial designation, A2017U1, reflected that assumption. A for asteroid, the rest encoding the year and discovery sequence. But as more observations came in, the calculations began to show something unusual. The path wasn't elliptical or even parabolic. It was hyperbolic, with an eccentricity significantly greater than 1. And the speed was high, about 26 kilometers per second relative to the Sun when it was already on its way out. That meant it hadn't slowed enough to be bound when it came in. Whatever this was, it came from outside and was already heading back into interstellar space. It was quickly reclassified and given a new name, 1am Oumuamua. The 1I marked it as the first interstellar object ever recorded, and the Hawaiian name, meaning scout or messenger from afar arriving first, was chosen to reflect its status and the location of its discovery by the Pan-STARRS telescope in Hawaii. By the time most of the world heard about it, Oumuamua was already too faint for detailed imaging, but the brief window we had was enough to cause a stir. Its brightness varied in a way that suggested a highly elongated shape, perhaps 6 to 10 times longer than it was wide, and it showed no obvious coma, no visible tail. It didn't behave like a typical comet, but neither did it match the reflective properties of most asteroids. That combination of strangeness and rarity drew attention far beyond the usual astronomical circles. Researchers proposed explanations ranging from a fragment of a larger body broken apart long ago, to a pancake-shaped shard, to a chunk of nitrogen ice from a Pluto-like world. A few even speculated about artificial origin, a thought experiment that caught headlines but remained unsupported by direct evidence. In truth, the limited data left room for multiple interpretations, and Oumuamua remains an object we know more for its mystery than for any settled facts. What it proved beyond debate, though, was that interstellar objects do exist, and we can detect them if we're watching closely enough. Just 2 years later, in August of 2019, the second one appeared. This time, the discovery was made not by a large professional survey, but by an amateur astronomer, Gennady Borisov, using a telescope he had built himself. From the first look, this new object showed a bright, fuzzy coma and a tail, a comet in both appearance and behaviour. It was given the name 2I Borisov, the second interstellar object confirmed, and the first to show clear cometary activity. Unlike Oumuamua, Borisov could be studied for months, and telescopes around the world and in orbit turned to follow it. Spectroscopic studies revealed a composition not unlike comets from our own solar system, though with some interesting differences. Its gases contained relatively high levels of carbon monoxide, suggesting it had formed in a very cold region around its home star, perhaps farther from its star than most comets in our system form from the Sun. The size was estimated at a few kilometers across, making it a substantial body compared to Oumuamua, which was likely only a few hundred meters at most. Borisov's appearance reinforced the idea that interstellar objects are diverse. One looked more like an asteroid, solid, dry, with no visible coma, while the other fit the classic image of an active comet. That diversity shouldn't be surprising. The galaxy is vast, and the processes that form and eject small bodies from planetary systems vary widely. What was surprising was the speed with which a second example appeared after the first. Before Oumuamua, astronomers might have expected to wait decades before seeing another. To have a second one in just 2 years suggested that these objects may pass through more frequently than we had guessed, and that our improved ability to detect faint moving points in the sky was paying off. Comparing the two also highlighted the importance of observation time. With Oumuamua, most of what we know comes from a few weeks of data taken after it was already past the Sun. By the time its interstellar origin was confirmed, there was no chance of mounting a spacecraft mission or even scheduling long, deep imaging campaigns. With Borisov, the discovery came early enough in its approach to allow extended monitoring. That difference gave astronomers a much clearer picture of its physical properties and composition. These two visitors also helped shape the search strategies for future ones. Surveys are now better tuned to flag high eccentricity objects quickly, and there's more coordination between observatories to confirm and follow up on suspicious trajectories. There's even been discussion of maintaining a standing mission design, a spacecraft ready to launch on short notice, so that if another interstellar object appears on a trajectory within reach, we could send a probe to intercept it. The idea is ambitious, given the speeds and limited warning times involved, but the scientific payoff of directly sampling material from another star system would be enormous. Beyond the technical details, Oumuamua and Borisov shifted the conversation about our place in the galaxy. Before them, most of what we knew about other planetary systems came from telescopes that detected planets indirectly, by their effects on their stars' light or motion. Now, we've had physical pieces of those systems pass right through our own. Even without touching them, analysing their light and behaviour gives us data we can't get any other way. They're not just points of light in distant orbits, they're travellers, bearing the histories of other worlds. This context makes 3I Atlas's appearance feel like a continuation of an unfolding chapter in astronomy, one that only began recently, but has already redefined what we expect to see in the night sky. The first time we spotted such an object, it was a surprise. The second time, it was a confirmation. The third time, it's starting to look like part of a pattern. Each one is different, but together they form the beginnings of a catalogue that will grow over the decades to come. It's worth remembering that all three were found by projects with different goals. Pan-STARRS was conducting a near-Earth object survey. Borisov was found by a dedicated amateur observer, and Atlas is focused on asteroid impact detection. None were designed specifically to search for interstellar visitors, yet all were capable of catching them. This suggests that as more survey capacity comes online, particularly with next-generation wide-field telescopes, we'll detect more, and with each detection, our picture of the galaxy's small body population becomes a little clearer. That's why looking back at Oumuamua and Borisov isn't just a matter of reminiscing about interesting discoveries. They set the stage for how we approach 3I Atlas, how quickly we recognise its significance, and how urgently we gather data before it slips away. They also remind us that while these visitors are rare, they are not once-in-a-lifetime events for the field as a whole. For individual observers, perhaps, but for the community, they are part of a growing list, each with its own trajectory, its own chemistry, and its own faint light crossing our detectors before heading back into the space between stars. The discovery of something like 3I Atlas rarely comes as a sudden shout of excitement in a control room. It's far more often a sequence of quiet, routine steps, each carried out by instruments that work tirelessly night after night. Atlas, the Asteroid Terrestrial Impact Last Alert System, is a set of automated telescopes designed for a specific and very practical purpose: finding objects that might collide with Earth. Its name reflects that mission. If something dangerous is coming our way, Atlas is meant to see it early enough to give a warning. That's the system's public face, but in carrying out that work it also records enormous amounts of data about all kinds of moving objects in the sky. The system's telescopes have wide fields of view, meaning they can take in large sections of the sky at once. Each clear night, they take multiple exposures of the same regions, separated by short intervals. The software compares these images, looking for points of light that shift position against the background stars. Those points could be asteroids, comets, space debris, or occasionally something else entirely. Every moving object is logged and measured, its brightness, position, apparent motion. That information goes into a central processing pipeline where automated routines sort the detections into likely categories. In April 2024, one of those detections didn't fit neatly into the expected patterns. At first, there was nothing obviously unusual about it. It was faint, just bright enough to be picked up in the exposures, and its motion was measurable but not extreme. The real clues emerged only after several nights of tracking. By plotting the positions and calculating the orbit, the team could see that it wasn't bound to the Sun. Its path was open-ended, a hyperbola rather than an ellipse. The eccentricity, a number that tells you how stretched the orbit is, was well above 1. That's the kind of result that demands closer inspection, because in most cases it means the object is interstellar. It's worth noting that astronomers are cautious with such declarations. Hyperbolic orbits can also occur when comets from the Oort cloud are perturbed by planets or by passing stars, giving them enough of a kick to escape. But the speeds involved are different. If an object has just barely enough energy to escape, its eccentricity will be only slightly above 1. With 3i Atlas, the numbers indicated it was travelling much faster than a comet ejected from our own system could be. That speed, combined with the incoming trajectory, was the evidence that convinced astronomers they were looking at another interstellar visitor. Once an object like this is flagged, the goal is to secure as many follow-up observations as possible. Atlas could only track it for part of the night, because the Earth's rotation and daylight limit the viewing window. The discovery alert was shared with the Minor Planet Center, which coordinates observations worldwide. Other observatories, both professional and amateur, turned their instruments toward the coordinates provided. Each new position measurement helped refine the orbit, making the interstellar origin more certain. In this stage, time is critical. These objects move fast, tens of kilometers per second relative to the Sun, and they can fade quickly as they recede from both the Sun and Earth. Every night without data increases the uncertainty in the orbit, making it harder to point telescopes accurately. That's why the discovery to confirmation process happens in days, not weeks. Once the data show the object is hyperbolic, and the speed confirms it's interstellar, astronomers know they have a limited window to study it. With 3i Atlas, the confirmation came quickly. The calculations were clear enough that the eye designation was assigned without delay, marking it as the third of its kind. That label immediately raised its profile. Astronomers who might not normally focus on cometary objects began requesting observation time. Even telescopes scheduled for other work can sometimes make a few exposures if an unusual target is in their part of the sky. This kind of cooperation is common in planetary science, where rare events are recognized as opportunities for everyone. The Atlas system itself is built on a principle that has become increasingly important in astronomy: wide field coverage and automation. Older surveys could only scan small sections of the sky each night, and much of the identification work relied on human review of photographic plates. Now, digital detectors and rapid processing make it possible to scan most of the visible sky multiple times per night, looking for changes. The computer routines can spot faint movers that the human eye might miss, especially when the movement is slow enough to be subtle in a single frame. That's how something as small and dim as 3i Atlas could be noticed at all. Its brightness at discovery suggested it was still on its inbound leg, not yet at its closest point to the Sun. That's valuable, because it means observers could watch its behaviour as it warmed. If it were icy, signs of activity might appear: a faint coma or tail, or changes in brightness caused by jets of gas. Early detection also allows astronomers to prepare for those changes, adjusting exposure times and instrument settings to capture the right kind of data. The way Atlas flagged it is also a reminder that most discoveries are incremental. The first night's detection wasn't enough to identify it as interstellar. It had to be linked to subsequent nights' detections and that linking depends on accurate timing and careful bookkeeping. The software predicts where the object should appear based on its motion so far, and then matches new detections to that predicted path. If the motion doesn't match known asteroids or comets, the object is added to a list of new objects needing further observation. It's only after several nights of consistent tracking that the unusual nature of the orbit emerges. Once the orbit for 3i Atlas was known, it was compared to databases of known objects and to the inbound paths of 1i Oumuamua and 2i Borisov. There was no connection. Each of these came from a different direction, with no evidence of a common source. That's what you'd expect if they were random samples from the galaxy's background population of small bodies. The distribution of their arrival directions can, in theory, tell us something about the structure of that population, but with only 3 examples, the statistics are too limited for strong conclusions. Even so, each one adds to the picture. The fact that Atlas found it also illustrates the value of having multiple survey systems with overlapping coverage. If one is clouded out or offline for maintenance, another can still watch the sky. This redundancy increases the chance of catching fast-moving faint objects before they pass beyond reach. In the case of 3i Atlas, the initial detection was strong enough that other telescopes could pick it up quickly, ensuring that the orbit solution improved rapidly. In the days after its confirmation, the object's coordinates were posted on public lists so that any capable telescope could contribute data. This is standard practice. Rare objects benefit from a broad network of observers because each observation adds precision to the orbit and sometimes reveals subtle changes in brightness or structure. For something moving this quickly, even a few hours difference in observation time between observatories can help constrain its path. The process of spotting an object like this is therefore not a single event, but a chain of coordinated steps. Detection by Atlas, recognition of unusual motion, orbital calculation, confirmation of interstellar status and worldwide follow-up, all within a short span of time. By the time most people heard the name 3i Atlas in the news, much of that work had already been done quietly, with the data flowing between survey teams, the Minor Planet Center, and individual researchers. For the scientists involved, this is where the real work begins. Once it's confirmed as interstellar, the next step is to decide what can be measured before it's gone. Spectroscopy to determine composition, photometry to study rotation and shape, high-resolution imaging if possible. Each type of observation requires specific conditions: brightness, sky position, telescope availability. Scheduling has to be fast and flexible because the window is measured in weeks or months at best. That urgency is one of the unspoken tensions in these discoveries. On one hand, there's excitement at seeing something so rare. On the other, there's the knowledge that every night brings it closer to leaving, and there will be no second chance. The history of 1i and 2i taught astronomers how quickly an interstellar object can fade from view, and those lessons shaped the rapid, coordinated response to 3i Atlas. Once the first few days of tracking confirmed that it was indeed from beyond the solar system, attention turned to the finer details that set it apart from almost anything else in the night sky. Even before the deeper analysis began, the sheer fact of its trajectory was enough to mark it as unusual. The orbit wasn't simply open-ended, it was steeply so, a clear hyperbolic path with a high excess velocity. That number, how fast it was moving relative to the Sun once free of its gravity, is one of the main indicators that we were seeing something not born here. Objects native to our solar system rarely reach such speeds unless they've been flung out by a close planetary encounter, and even then the velocity tends to hover just above escape level. This one had much more energy to spare. That alone would have made it notable, but the way it behaved as it approached the inner solar system deepened the interest. At the time of its discovery it was faint and distant, inbound but not yet near enough for the Sun's heat to produce dramatic changes in its appearance. This gave astronomers a chance to monitor it through that warming phase. In most comets, especially those that have spent long stretches in deep space, sunlight triggers the sublimation of surface ices, releasing gas and dust into a surrounding coma. The strength, composition, and timing of that activity can reveal much about the object's makeup and its thermal history. In the case of 3I Atlas, early indications hinted at some cometary activity, but it wasn't the kind of vigorous outgassing that produces bright tails. Instead, the changes were subtle, small increases in brightness, slight indications of an extended shape in images taken with larger telescopes. For something that has spent millions of years in interstellar space, those signs matter. They tell us that despite the harsh environment between the stars, bombarded by cosmic rays, subjected to temperature extremes, it has retained enough volatile material to respond to the sun's warmth. That survival alone is remarkable, because interstellar travel is not gentle. Its faint activity also raised questions about its surface. A dark, dusty crust could insulate the interior, delaying the release of gas until deeper layers are warmed. If the crust has been thickened by long exposure to radiation, it might alter the timing and amount of visible activity. Comparing that behaviour to comets from our own solar system can hint at whether its home environment was similar or very different. For example, the presence or absence of certain volatiles could reflect the distance from its parent star where it formed. Another unusual feature was the challenge of estimating its size. Without a well-defined coma, the brightness we see is mostly from reflected sunlight off the solid nucleus. But brightness depends not only on size but also on reflectivity, or albedo. A small, highly reflective object can appear as bright as a larger, darker one. With 3I Atlas, the range of possible sizes was wide, from a few dozen meters to a few hundred, depending on assumptions about its surface. The uncertainty is not surprising for something so distant and faint, but it adds to the difficulty of pinning down its physical nature. The shape and rotation are equally tricky to determine but equally telling. For objects this small and far away, even the largest ground-based telescopes can't resolve them as anything other than points of light. Instead, astronomers watch for periodic variations in brightness as the object spins. A long, thin body like Oumuamua will show large swings in brightness during a rotation, while a more spherical body produces smaller changes. For 3 Atlas, the early light curves were not yet conclusive, but there were hints of irregularity, something more complex than a smooth, even spin. That could mean a non-spherical shape or even a tumbling motion, both of which would be consistent with a history of collisions or close passes with other bodies long before it entered our solar system. Its incoming direction also made it stand out. By projecting its trajectory backward, astronomers found it was arriving from a part of the sky that didn't align with any specific known stellar system as an origin. This wasn't surprising. Over the millions of years it has been travelling, it could have been nudged by multiple gravitational encounters, but it underscores the randomness of its arrival. Unlike spacecraft we launch on carefully planned paths, interstellar objects are on wandering journeys shaped by the accumulated effects of distant encounters. The lack of a clear source star also hints at how common these wanderers might be. If every planetary system ejects some fraction of its small bodies over time, the galaxy could be filled with them, moving in every direction. We're only now reaching the sensitivity to detect the ones that happen to pass within observational range. Each detection is therefore a statistical sample of a much larger population we can't yet see. That population is an important piece of the puzzle in understanding how planetary systems evolve and exchange material. On the technical side, the unusual brightness pattern of 3I Atlas complicated predictions for its future visibility. Normally, astronomers can forecast how a comet's brightness will change as it approaches and recedes from the Sun by comparing it to similar objects. But with interstellar comets, there's no guarantee those models apply. Different chemical compositions, different surface properties, and different histories can all lead to unexpected changes. That unpredictability means observers must adapt quickly, sometimes revising exposure times or observation schedules based on new data from just the night before. Another factor in its uniqueness is simply its rarity as a confirmed interstellar object. Even with 2 previous examples, each new one is an opportunity to expand the range of known properties. Oumuamua and Borisov showed us 2 very different cases, one dry and elongated, the other active and more comet-like. 3i Atlas falls somewhere between those extremes, with faint activity but not a spectacular tail, with a trajectory that's clearly interstellar but a physical profile that resists easy classification. This in-between nature makes it a valuable data point, because it shows that interstellar visitors don't fit into just 2 categories. The speed with which it crossed the inner solar system also stands out. At its closest to the Sun, it would still be moving too fast for any realistic intercept mission launched after discovery. That limitation is a reminder of how challenging it will be to study such objects up close. Spacecraft need years of planning and flight time to match speeds with distant targets. Unless one is already waiting in the right place, these fleeting visitors will remain beyond our reach physically, leaving us to rely entirely on remote sensing. This makes every photon of light they reflect or emit into our telescopes worth capturing and analysing. There's also an underlying oddity in the way it entered our awareness at all. The only reason we could see it was because of the constant vigilance of survey systems like Atlas. And the only reason Atlas exists is because of the need to detect potentially hazardous objects. In that sense, the infrastructure built for planetary defense is also serving as our window onto the broader galaxy. It's a reminder that tools built for one purpose often end up answering questions their designers never anticipated. Taken together, these elements, the hyperbolic speed, the faint but real signs of activity, the uncertain size and shape, the ambiguous brightness pattern, the random arrival direction, paint a picture of an object that doesn't slot neatly into any of our existing categories. It's not enough to say it's a comet or an asteroid. It's something that carries aspects of both, shaped by an origin and a journey we can only infer. That ambiguity is part of what makes it so unusual, because most objects we study in detail belong to well-understood groups. Here, we have a single example of a type we're only beginning to define. Each observation is an attempt to move it from unusual to understood, even knowing that by the time those analyses are complete, the object will be far beyond the reach of our telescopes, leaving only the record of its brief appearance in our sky. By the time it first appeared in our data, 3i Atlas had already completed a journey so long and so unbroken that no instrument or record exists to trace it fully. We can calculate its incoming direction, estimate its speed in interstellar space, and make educated guesses about the conditions it experienced, but the majority of its history is locked in the silence of deep time. Even so, the information we do have allows us to sketch a picture, not with fine details, but with enough structure to understand that this is not a recent traveller. The trajectory tells us it came from far beyond the outer edges of our solar system. Long before it crossed the sphere of space influenced by the Sun's gravity, it was already moving on a path shaped by encounters in another star system. Objects like this are thought to be born in the distant outskirts of planetary systems, in regions roughly analogous to our own Oort cloud or Kuiper belt. Those are zones filled with icy bodies, leftovers from the era of planet formation. In stable conditions, such objects can remain in place for billions of years, orbiting far from their star. But planetary systems are not static environments, and over time gravitational nudges from giant planets or passing stars can disrupt those orbits. For an object to be ejected completely, a significant gravitational event has to occur. One possibility is a close pass with a massive planet early in the system's history, when orbits are still settling and large bodies migrate inward or outward. Another is the influence of a nearby star, either in the system's birth cluster or during a later close encounter in the galaxy. In either case, the effect can be enough to accelerate the object past escape velocity, sending it out of its home system on a one-way trajectory into interstellar space. If this happened to 3i Atlas, it would have left behind its original neighbours forever, trading a stable orbit for an open-ended drift among the stars. Once free, its speed relative to the galaxy would be set mainly by that final gravitational push and the motion of its home star through the Milky Way. From then on, it would move under the influence of the galaxy's overall gravitational potential, following a path curved gently by the combined mass of billions of stars, clouds of gas and dark matter. Over millions of years, it might have passed near other stars or through denser regions of the galaxy, but space is vast, and the probability of another strong gravitational deflection is small. Most of its travel would have been through regions so empty that it could have gone centuries without passing within even a few astronomical units of another object. In that environment, the conditions are extreme but unchanging. Temperatures hover only a few dozen degrees above absolute zero. There is no sunlight to warm it, no nearby source of heat at all. Cosmic rays, high-energy particles from distant sources, would strike its surface constantly, slowly altering the chemistry of exposed materials. Over long timescales, this radiation can darken and harden the surface, forming an insulating layer that may help preserve volatile ices beneath. Impacts from tiny dust particles, moving at tens of kilometers per second, would occasionally pit or chip away at that crust, but such events would be rare compared to what objects experience in denser regions like asteroid belts. If 3i Atlas is indeed a cometary body, much of its time in interstellar space would have been spent in a kind of suspended state. Its interior would remain almost entirely unchanged from the moment it left its home system, while its surface slowly accumulated the signs of long exposure to radiation and micrometeoroid impacts. This is part of why studying it now is so valuable. It is, in a sense, a sealed container holding material from a place we cannot otherwise reach, preserved by eons of isolation. The direction from which it entered our solar system offers a broad clue about its past motion. By tracing its path backward relative to the local standard of rest, a reference frame based on the average motion of nearby stars, astronomers can see whether its trajectory aligns with any known stellar neighbourhoods. In this case, the uncertainties are too great to identify a specific star as its origin, but the motion is consistent with the idea that it has been travelling independently for millions of years, perhaps longer. The galaxy's constant slow stirring of stars and interstellar material means that any memory of its exact launch point has been erased. At the scale of its journey, the time it will spend in our solar system is vanishingly small. Even travelling at tens of kilometers per second, it would take tens of thousands of years to cross just the distance between stars in the Sun's immediate vicinity. The few months during which we can observe it up close are less than an instant in comparison. That mismatch in timescales is part of what makes these encounters so fleeting. Objects like 3i Atlas are almost always somewhere far from any star, and only occasionally pass close enough to one for anyone to notice. The odds of it passing near Earth are not a result of any special targeting. There's no mechanism guiding it toward us. Instead, it's a statistical inevitability that, given enough time, some fraction of interstellar objects will intersect the small volume of space occupied by our planets. The vast majority will not come close enough to detect, but those that do give us a brief chance to learn from them. That chance depends entirely on our ability to watch large swathes of the sky and recognise when something's path is unusual. Without that capability, 3i Atlas would have entered and left our region of space without any record of its passing. One of the challenges in reconstructing its journey is the lack of any visible trail. Within the solar system, comets can sometimes be tracked by the dust they shed, which lingers along their orbits. In interstellar space, such dust disperses quickly, and the distances are too great for it to remain concentrated. Whatever fragments or particles 3i Atlas may have lost over the millennia are now far scattered, indistinguishable from the background grains that drift between the stars. Its motion now is that of a solitary body, carrying no companions and leaving no path to follow back. The possibility that it has passed near other stars raises interesting questions. Each such pass, even at a great distance, can alter an object's trajectory slightly. Over time, these small changes accumulate, meaning that even if we knew its starting point with perfect accuracy, the path back would be blurred by countless minor influences. In this way, interstellar objects are like messages with their envelopes worn and the postmarks smudged. What remains is still valuable, but the route it took to get to us is no longer fully legible. It's also worth considering that its time in interstellar space might not have been spent entirely in darkness. If it passed through the outer reaches of another star's planetary system, it might have been warmed slightly, though not enough to cause major changes. Passing through denser clouds of interstellar gas could have deposited trace materials on its surface. Over millions of years, these small events can add layers of complexity to the story it carries. Each one leaves microscopic clues that, in principle, could be read if we had a sample in hand. From Earth, those clues are reduced to faint spectral lines in the light we collect. By the time it crossed the outer boundary of the solar system, the region where the sun's gravity becomes the dominant influence, it would have been moving fast enough that even the slow pull inward barely changed its overall speed. The sun bent its path, but not enough to capture it. Inbound, it began to accelerate slightly under that pull, heading toward the region where our telescopes would eventually detect it. That final approach, from the outskirts of the solar system to its discovery by Atlas, may have taken only a few years. Compared to the millions of years of wandering that came before, this last leg is almost too brief to measure. The first step after confirming that it was on a hyperbolic path was to begin a systematic campaign of measurements. These early observations are the foundation for everything that follows. They determine how well we can predict its future path, how much we can learn about its physical properties, and whether there's enough time to catch any changes in its behaviour as it approaches and recedes from the sun. The key is to begin immediately, because each night lost reduces the accuracy of orbital predictions and narrows the opportunity to study it under different conditions. Position measurements, known as astrometry, are always the priority. These are precise records of where the object appears against the background stars at a given moment. Even small errors can make a big difference when projecting the path weeks or months into the future. For 3i Atlas, observatories in different parts of the world contributed to this task, allowing continuous coverage despite Earth's rotation. By combining positions taken at widely spaced locations, astronomers could refine the orbit quickly, reducing uncertainties in both the inbound and outbound trajectories. At the same time, photometry began, systematic measurements of its brightness over time. Photometry does more than tell us how bright the object is. It reveals patterns that can be linked to rotation, shape, and activity. If the object spins, the amount of sunlight it reflects will vary as different surfaces turn toward and away from us. The amplitude and period of those variations can suggest whether it's elongated, irregular, or roughly spherical. In the first days after its discovery, photometric data hinted at changes in brightness, but the signal was faint, and more measurements were needed to be certain. Spectroscopy was another immediate goal. By splitting the light from 3i Atlas into its component wavelengths, astronomers could look for signatures of specific molecules or minerals. For comets, this often means detecting gas emissions from sublimating ices, such as water, carbon dioxide, or carbon monoxide. The presence and relative strength of these lines can reveal the composition and temperature history of the object. In 3i Atlas's case, early spectra suggested some outgassing, but at a much lower level than in typical active comets from our own solar system. This matched the subtle visual signs, faint fuzziness around the nucleus rather than a bright extended coma. Collecting these spectra was not straightforward. The object's faintness meant that only large telescopes with sensitive instruments could gather enough light for analysis. That required coordination and scheduling, often at short notice, because major observatories plan their observing runs months or years in advance. The confirmation of 3i Atlas's interstellar nature helps secure time, as such opportunities are rare enough to justify interrupting other programs. Another challenge in these early measurements was the object's motion relative to the stars. At its distance and speed, 3i Atlas moved perceptibly even over the course of a single long exposure. Without tracking the telescope at the same rate, the object's light would smear across the detector, reducing the quality of the data. Specialized tracking modes allowed telescopes to follow its exact path, keeping it sharp while the background stars streaked instead. This inversion of the usual imaging approach is standard for fast-moving objects, but requires precise predictions of their positions for the duration of the exposure. In addition to these core methods, astronomers also used polarimetry, which measures the polarization of light reflected from the object's surface or coma. Polarization can be sensitive to the size and composition of dust grains, offering another angle on the physical properties. For 3i Atlas, the polarization data were sparse but valuable, adding detail to the picture that spectroscopy and photometry alone could not provide. The first thermal measurements came from infrared observations. While visible light tells us about reflected sunlight, infrared wavelengths can reveal how much heat the object emits, which in turn can be used to estimate its size and albedo. In practice, this is difficult for faint small objects far from the sun, but space-based infrared telescopes can sometimes detect them if they're bright enough. Early attempts with 3i Atlas aimed to place limits on its diameter and reflectivity, narrowing down the possible combinations of size and surface properties. As the data accumulated, the object's unusual behavior became clearer. The activity level was lower than in a typical comet at a similar distance from the Sun, yet it was higher than in completely inert asteroids. This intermediate state added weight to the idea that interstellar objects span a spectrum of properties, rather than fitting neatly into categories familiar from our own solar system. In practical terms, it meant astronomers had to be ready for its appearance to change unpredictably as it moved closer to the Sun. The rotation period, a critical parameter for understanding its shape and internal structure, remained elusive in the first weeks. The variations in brightness were subtle, and the viewing geometry meant that certain orientations could hide or diminish the expected signal. Observers kept collecting photometry night after night, knowing that as the geometry changed, the variations might become more pronounced and the period easier to determine. For some, the earliest images of 3i Atlas carried an added sense of significance simply because they were the first. Even as tiny points of light on a detector, they represented the start of a record that would grow over the weeks to come, a record that would eventually be all that remained once the object was gone. In a field where many observations are routine and predictable, the chance to measure something completely new brings a different kind of focus to the work. These first measurements also set the stage for all later analysis. The initial astrometry locked in the orbit, ensuring that no one would lose track of it. The early photometry established a baseline for its brightness and activity, allowing later changes to be measured against that reference. The first spectra gave a starting point for tracking the evolution of its composition under solar heating. Without these, later data would have less context, and the interpretation of its behavior would be less certain. Once the orbit was securely established and the initial photometry provided a baseline, attention shifted toward the questions of physical form. Knowing the shape, size, and spin of a small, distant object is not as simple as pointing a telescope at it and taking a picture. For something like 3i Atlas, which appears only as a point of light in even the most powerful ground-based instruments, these properties have to be inferred indirectly, using variations in brightness over time and, when possible, thermal measurements that give clues about its dimensions. The first step in understanding its shape came from analysing its light curve. As the object rotates, the amount of sunlight it reflects changes depending on the orientation of its surface toward Earth. A perfectly spherical object with a uniform surface would reflect the same amount of light throughout its rotation, producing a flat light curve. Any variation indicates either an irregular shape, differences in surface reflectivity, or both. For an elongated object, the change in brightness can be significant, with peaks when the long side faces us and troughs when we see it end on. In the early days of observation, the photometric data for 3i Atlas were too sparse to produce a clear rotation period. The variations in brightness were present but subtle, suggesting either a shape that was not highly elongated or a rotation axis aligned in a way that minimized changes from our perspective. Another possibility was that the surface was relatively uniform in reflectivity, muting the amplitude of brightness fluctuations. Continued monitoring was needed, as changing viewing geometry during its approach could reveal stronger signals. Size estimation was even more challenging. The brightness we measure depends on both the size of the object and its albedo, the fraction of sunlight it reflects. A small, highly reflective body can appear as bright as a larger, darker one. Without direct imaging or radar measurements, astronomers had to make educated guesses about the albedo based on analogues from our solar system. For comets, typical albedos are low, reflecting only a few percent of the sunlight that hits them. If 3 Atlas had a similar surface, its measured brightness would imply a nucleus perhaps a few dozen to a few hundred meters across. But if its surface was brighter or darker than average, the size could be substantially different. Infrared observations offered a potential way to break this degeneracy. By detecting the object's thermal emission, astronomers could estimate how much sunlight it absorbed and re-radiated as heat, which in turn constrains its size and reflectivity. However, given the faintness of 3i Atlas and the limitations of available infrared instruments, this was a difficult task. Even the most sensitive space-based detectors would struggle to pick up a clear signal at its distance. Attempts were made, and while some data were collected, they were more useful for setting upper and lower limits than for pinpointing an exact diameter. Determining the spin rate was another priority, as it provides insight into the object's structural integrity. Rapid rotation could mean that it is held together by internal strength rather than just gravity, or that it is a single solid piece rather than a loose aggregate of material. Very slow rotation could indicate a history of torques from outgassing or past gravitational interactions. For 3 Atlas, the preliminary indication suggested a moderate rotation period, but the uncertainties were still large. The faintness of the signal and the influence of activity, small amounts of dust or gas that can affect the measured brightness, made it difficult to separate rotational effects from transient changes in the coma. In comparing it to previous interstellar visitors, the differences were notable. Mwama showed large brightness variations, consistent with a highly elongated shape or an extreme aspect ratio, and had a rotation period of several hours. Borisov's brightness changes were dominated by its active coma, making it harder to isolate the nucleus's rotation. 3i Atlas seemed to occupy an intermediate ground, with modest variations that could point to a shape closer to spherical or to a viewing angle that obscured its elongation. This middle ground fit the broader pattern emerging from these discoveries. Interstellar objects are not all the same, and each one so far has displayed its own mix of characteristics. The possibility of tumbling, rotation about more than one axis, was also considered. Tumbling can result from past collisions, uneven outgassing, or gravitational interactions, and it tends to complicate the light curve by introducing multiple overlapping periods. If 3i Atlas were tumbling, it would make the interpretation of its photometric data more complex, but could also provide clues about its past environment. A stable, single-axis rotation would suggest that it has been in a relatively calm state for a long time, while tumbling would imply a more eventful history. Surface properties also factored into the interpretation of size and shape. The reflectivity could vary across the surface, producing brightness changes unrelated to geometry. For example, patches of fresh ice exposed by recent impacts or thermal cracking would be brighter than surrounding darker areas. If such features existed on 3i Atlas, they could mimic the effect of an elongated shape or even mask it, depending on their distribution. Spectroscopy offered some hints about surface composition, but at the resolution available, it could not map variations across the object. Radar, which has been used to map the shapes of near-Earth asteroids in great detail, was out of the question for 3i Atlas. Its distance and small size made it far too faint for current planetary radar systems, even with the most powerful transmitters. This limitation meant that all size and shape estimates had to rely on indirect optical and thermal methods, each with its own uncertainties. As the observational campaign continued, the combined data began to narrow the possibilities. The light curve suggested a rotation period likely between several hours and a day, with no evidence yet of extremely rapid or slow spin. The brightness range indicated that if it was elongated, the ratio of its longest to shortest axis was modest, perhaps 2:1 rather than the more extreme shapes seen in some asteroids and inferences for Oumuamua. This placed it closer in appearance to the average comet nucleus, albeit with the added twist of being from another star system. The fact that it showed some activity without being dominated by it allowed for more accurate size constraints than in the case of Borisov. By modelling the contribution of the faint coma to the total brightness, astronomers could isolate the nucleus's share and refine estimates of its diameter. While the numbers were still not precise, the consensus pointed to something in the lower hundreds of meters across, large enough to survive its long journey intact, but small enough to be typical of the population of icy bodies at the fringes of planetary systems. In all of this work, patience was as important as instrumentation. The changes in viewing geometry as Earth and the object moved along their orbits gradually provided better conditions for measuring rotation and shape. Each night's data built on the last, and even small improvements in signal quality could shift the favoured models. The team effort spanned continents and hemispheres, with northern and southern observatories covering different parts of its trajectory to maximise the number of usable observations. By the time these measurements had accumulated into a coherent picture, 3i Atlas was already well along its inbound path, approaching the point where it would be nearest to the Sun. This stage would bring its own set of observations, watching to see whether heating triggered increased activity, whether the light curve changed as jets of gas altered its rotation, and whether the overall brightness behaved according to cometry norms or continued to surprise. The shape, size, and spin determined in this pre-perihelion phase would serve as the baseline for tracking any changes during and after its closest approach, a way to measure the effects of a brief encounter with our star on a body that had spent nearly all of its existence in the cold between the stars. Once the first estimates of its dimensions and rotation were in place, the focus turned toward what could be learned about the actual substances making up this visitor. In astronomy, direct sampling is an extraordinary rarity. For most objects beyond the reach of spacecraft, composition has to be deduced from the light they reflect and emit, and from the way they interact with their environment. For 3i Atlas, the most important tools for this were spectroscopy and careful monitoring of its activity. Spectroscopy works by spreading out the light from the object into a spectrum, revealing patterns of brightness at different wavelengths. Some patterns are the result of sunlight reflecting off the surface, while others are caused by gases or dust released from the surface as it warms. Specific molecules absorb and emit light at characteristic wavelengths, so even faint signatures in a spectrum can point to the presence of certain materials. For comets in our own solar system, common detections include water vapour, carbon monoxide, carbon dioxide, and various carbon-based compounds. Each of these tells a story about the conditions in which the comet formed, because their stability depends on temperature and pressure. In the early spectra taken of 3i Atlas, there were hints of gas emissions, though the lines were faint. The most promising candidates were from cyanogen, Cn, and possibly diatomic carbon, C2, both of which are common in cometary comae. The detection of Cn in particular was important. It suggested that, like many comets from our own Oort cloud, this object contained organic compounds that could break apart under solar radiation to produce the observed lines. The presence of these species implied that the body still had volatile materials near its surface, despite the immense timescale it had spent in the interstellar medium. This resilience raised immediate questions about how deeply the cosmic ray-induced crust extended. In interstellar space, the constant bombardment of high-energy particles is expected to process and erode volatile-rich surfaces, creating a hardened layer meters thick in some cases. If 3I Atlas still retained accessible volatiles, it might mean that impacts or other events had exposed fresh material more recently in its history, or that the crust was thinner than expected, allowing the sun's heat to reach ice reserves relatively quickly after entry into our system. Further observations sought to detect water vapor directly. Water is the dominant volatile in most comets, but its spectral lines are harder to measure from the ground due to interference from Earth's atmosphere. Space-based observatories have a better chance, and efforts were made to secure observing time on platforms capable of working at infrared wavelengths where water lines appear. While the data were still being analysed during its apparition, the mere possibility of detecting water from an interstellar body carried strong implications for how planetary systems beyond our own distribute and preserve such material. The dust released by 3I Atlas was also a key to its composition. By measuring the brightness and spectrum of the coma in reflected sunlight, astronomers could estimate the size distribution of dust grains and, in some cases, their mineral content. For example, silicate minerals have characteristic features in the infrared that can be identified if the signal is strong enough. Comparing these dust properties to those of known solar system comets offers one of the few ways to see whether the chemistry of distant planetary systems produces similar materials. In this case, the dust appeared broadly similar to that in long-period comets, though the uncertainties remained large due to the faintness of the coma. One of the more speculative questions was whether isotopic ratios, such as the ratio of deuterium to hydrogen in water, could be measured. These ratios are fingerprints of the environment in which ices form, influenced by temperature, pressure, and the radiation field. In principle, detecting an unusual isotopic ratio in 3I Atlas could confirm that it formed under conditions different from those in the solar nebula. In practice, such measurements are at the limits of current capabilities for such a faint and distant object, and would require exceptional observing conditions and instrumentation. The analysis also considered the possibility of more exotic compositions. Interstellar space could harbour bodies with mixtures of volatiles not found in our own system, perhaps due to different star types or planetary arrangements in their birthplaces. Ammonia-rich ices, hydrocarbons with unusual chain lengths, or sulfur-bearing species could all be candidates, though none were definitively detected in 3I Atlas during the initial campaigns. Even so, the absence of strong signatures of some volatiles was informative. It suggested that, if present, they existed in low abundance compared to the more common cometary materials. As with many small bodies, the composition was not uniform in the data. Slight changes in the relative strength of emission lines over time hinted that outgassing was coming from localized regions rather than the entire surface. This patchiness could be the result of uneven heating due to rotation, or of variations in surface crust thickness and composition. If the active regions were concentrated, they might also produce small torques that could alter the rotation state over time, a phenomenon observed in many solar system comets. Polarimetric observations of the coma provided another piece of the puzzle. The polarization of scattered light depends on the size and composition of the dust particles, and in 3I Atlas it was consistent with a mixture of fine and coarse grains, much like those seen in solar system comets. This again suggested that, despite its alien origin, its dust properties were not radically different from what we are familiar with. Such similarities point towards certain universal aspects of planetesimal formation, implying that the processes shaping comets may operate in broadly similar ways across the galaxy. The question of whether 3I Atlas contained any complex organic molecules was harder to answer. These molecules have distinctive spectral features, but detecting them at the required sensitivity was beyond the reach of most ground-based instruments. Nonetheless, the detection of CN and C2 hinted that organic precursors were present, and if so, they may have been preserved since the object's formation. That in itself carries significance for studies of prebiotic chemistry, since it means the building blocks of life can survive the harshest environments over interstellar timescales. The final composite picture from these composition studies was necessarily incomplete, but it still provided a rare insight into matter from another star system. A nucleus likely made of water ice, carbon-based compounds, and silicate dust, covered by a radiation-processed crust, with active regions that release gas and dust when warmed. This was a scenario that fit the available data. It was not an exotic object made of unfamiliar substances, but rather one whose basic components echoed those found in comets we've studied for decades. The differences lay in the details, in the ratios of materials, in the fine structure of the dust, and in the long record of interstellar exposure etched into its surface. With the broad outline of its physical makeup established, the focus turned more deeply to its motion through the solar system. An object's path is as much a part of its identity as its size or composition, and in the case of 3I Atlas, that path carried the signature of its interstellar origin as clearly as any spectroscopic measurement. Orbital calculations confirmed what the early astrometry had hinted at. This was not a closed loop around the Sun. It was not an ellipse, nor even the elongated ellipse of a long-period comet. Its orbit was hyperbolic, a curve that would carry it in and then back out, never to return. This hyperbolic shape is defined mathematically by its eccentricity, a parameter that describes how much an orbit deviates from a perfect circle. For circular orbits, the eccentricity is 0. For ellipses, it lies between 0 and 1. A parabolic orbit, right at the threshold of escape, has an eccentricity of exactly 1. Anything greater than 1 is hyperbolic, meaning the object has enough energy to escape the Sun's gravity entirely. For most comets and asteroids within our solar system, eccentricities greater than 1 are rare and usually temporary, caused by gravitational interactions with planets. But 3 Atlas's eccentricity was well above 1, leaving no doubt that it had arrived from far beyond the Sun's domain. Alongside eccentricity, astronomers measured its hyperbolic excess velocity, the speed it would have after leaving the Sun's influence. This velocity is an important clue, because it can be compared to the distribution of speeds of stars and interstellar material in the solar neighbourhood. In this case, 3 Atlas's excess velocity placed it comfortably within the range expected for an unbound object drifting through the galaxy, moving under the general gravitational field of the Milky Way. It was not unusually fast or slow, which suggested that it was not the result of an extreme ejection event or a recent close stellar encounter. Instead, it was likely a long-term traveller, its motion shaped by the slow accumulation of influences over immense timescales. Tracing the path backward into space is a more uncertain process. Over the millions of years it may have spent in interstellar space, tiny gravitational nudges from passing stars or clouds of gas could have shifted its trajectory by small but cumulative amounts. In principle, if a recent encounter with a nearby star were responsible for sending it toward our solar system, astronomers could match its incoming direction to that star's position in the past. In practice, the further back one projects, the larger the uncertainties become. For 3I Atlas, no clear candidate emerged. Its inbound direction did not align neatly with any known stellar system at the right distance and velocity, reinforcing the idea that it had been on this path for longer than we can reconstruct. The inclination of its orbit, the tilt relative to the plane of the solar system, was another telling feature. While many comets from our own Oort cloud arrive on steeply inclined paths, the distribution of inclinations for interstellar objects is essentially random, reflecting the fact that their origins are scattered across the galaxy. 3I Atlas's inclination fit this expectation. Its approach came from a direction that placed it well out of alignment with the major planetary orbits, which helped in one sense. It minimized the chances of a close gravitational encounter with a planet that could complicate its trajectory, before detailed observations were completed. One aspect of its path that drew attention was the timing of its discovery relative to its perihelion, the point in its orbit closest to the Sun. Ideally for study, an interstellar object would be found long before perihelion, allowing months of inbound monitoring before it reached peak activity. For 3i Atlas, the discovery came while it was still inbound, but not far from perihelion, compressing the timeline for certain types of measurements. This is one of the recurring challenges in the study of interstellar visitors. They move quickly, and spotting them early enough to mount a comprehensive observing campaign requires constant sky coverage and rapid follow-up. Despite these timing constraints, the measured path offered some advantages for study. Its trajectory brought it into a range where both northern and southern hemisphere telescopes could observe it, allowing for nearly continuous coverage during the most critical phases. The relatively close perihelion distance meant that solar heating would be strong enough to drive activity, providing a clearer look at its volatile content, but not so close that it would become inaccessible due to the sun's glare for extended periods. There were also subtle details in its path that helped refine models of its motion. Non-gravitational forces, such as those caused by jets of gas venting from the surface, can alter a small body's trajectory slightly over time. These effects are routinely measured in active comets and can provide indirect evidence of rotation, mass, and the distribution of active areas. For 3i Atlas, early attempts to detect such deviations from a purely gravitational path produced mixed results. Any non-gravitational acceleration appeared to be small, consistent with the low activity levels seen in imaging and spectra. From a dynamical perspective, the path of 3i Atlas through the solar system was straightforward. It came in on a hyperbola, passed the Sun at a modest distance, and would leave again on a mirror image hyperbola in the opposite direction. But from the perspective of planetary science, every detail of that path had value. It confirmed its origin beyond the solar system. It placed constraints on how it could have been ejected from its home system. It revealed that it was not an unusually high-speed object, and thus not likely to have been accelerated by a recent catastrophic event. It demonstrated that interstellar visitors can and do pass through the solar system on a variety of inclinations, speeds, and perihelion distances, meaning that future discoveries will come from many different parts of the sky. Even the outbound leg of its path would have significance. Observers planned to continue monitoring it as long as possible after perihelion to see whether activity persisted, faded quickly, or changed in character. Any measurable shift in its trajectory on the way out could provide further evidence of non-gravitational effects. The outbound arc also offered a chance to see different regions of the surface illuminated as the viewing geometry changed, potentially revealing new active areas or variations in colour and brightness. As much as this path told us about its nature, it also underscored the limits of our current capabilities. An object discovered at this stage in its journey cannot be intercepted by any spacecraft we have today. The speeds involved are far greater than what our fastest missions have achieved, and the time from discovery to closest approach is too short to design and launch a mission. This reality means that for now our role is that of distant observers, gathering as much data as possible while the opportunity lasts, and preparing for the possibility that one day we might catch such an object earlier when a close-range study is feasible. The question of whether something like 3i Atlas could carry life is one that inevitably comes up, even among astronomers who approach the subject with a careful, data-driven mindset. It is not about expecting to see signs of thriving ecosystems or advanced biology. There is no reason to believe that a small icy body drifting between stars would host anything like that. Instead, the discussion centers on whether it could preserve microscopic life, or at least the molecular precursors to life over the immense timescales of its journey. The idea has a name: panspermia. In its simplest form, panspermia suggests that life, or the building blocks of life, can be transported across space by natural means. It is not a claim that this is common, only that it is physically possible. Within our own solar system, we know that fragments of Mars have landed on Earth, ejected by asteroid impacts and travelling through space before falling into our atmosphere. Some of those rocks were launched with minimal heating at their cores, raising the possibility that hardy microorganisms could survive such a trip. Extending that concept to the interstellar scale is a much greater leap, but not an impossible one from a purely physical standpoint. The main challenge to survival over interstellar distances is time. Even at tens of kilometers per second, crossing from one star to another takes tens of thousands of years at minimum, and for objects like 3I Atlas, the journey could be millions of years long. Over such timescales, the surface of the body is constantly exposed to cosmic rays, ultraviolet light from distant stars, and occasional impacts from dust grains. These are lethal conditions for unprotected life as we know it. However, if microscopic organisms or organic molecules were buried deep within the object, shielded by meters of rock or ice, they could be insulated from the worst of this radiation. Laboratory experiments have shown that certain hardy spores can survive in a dormant state for years under vacuum and radiation when adequately shielded, though extending that to geological timescales remains speculative. For 3 Atlas specifically, there is no evidence that it carries life, and no realistic way to test for it from Earth. But the detection of organic compounds such as CN and C2 in its coma is enough to remind us that these building blocks are widespread in the universe. Organic chemistry happens in interstellar clouds, in protoplanetary disks, and on the surfaces of icy bodies throughout planetary systems. Whether these compounds can be assembled into something more complex, and whether that complexity can survive interstellar travel are open questions. Some scientists view interstellar comets like 3I Atlas as potential couriers for these compounds between star systems. In this view, the ejection of a comet from a planetary system is not just a matter of gravitational dynamics, it is also the dispersal of that system's chemical signature into the galaxy. If those comets encounter another planetary system, perhaps falling toward a young planet with a suitable atmosphere, they could deliver their stored organics as part of the raw material for new biochemistry. The amounts involved would be small on a planetary scale, but chemistry does not require large quantities to begin. In this context, 3 Atlas becomes not just a curiosity, but a representative of a much larger unseen population. If our solar system can eject icy bodies, and we have good reasons to think it can, then countless other systems must be doing the same. The galaxy could be filled with a slow but constant exchange of such objects, each carrying a frozen record of its birthplace. Some might carry only unremarkable ice and dust, others might hold rare molecules or unusual mixtures. A few could, in principle, harbour dormant microbial life if conditions in their parent systems allowed it to form and survive. The possibility also raises questions about the origin of life on Earth. While the dominant scientific view is that life arose here from local chemistry, panspermia remains a theoretical alternative, that life or its components could have been seeded from elsewhere. The detection of interstellar objects is still too new for us to assess how plausible this pathway might be, but each one we observe adds to the picture of what kind of material is actually moving between the stars. So far, that material looks chemically compatible with life as we know it, even if it shows no direct signs of it. Radiation damage is the strongest counter-argument against long-term survival. Cosmic rays can penetrate even thick shielding over time, gradually breaking down complex molecules and damaging cellular structures. An icy crust can slow this process, and the deeper the burial, the better the protection. If 3I Atlas has a radiation-processed crust several meters thick, anything beneath that depth could have been well protected since its ejection. Whether that protection is enough over millions of years is unknown, but the principle is sound enough to keep the idea from being dismissed outright. Another consideration is the thermal environment during ejection. For a comet to be thrown out of its home system, it might pass close to a giant planet or even its star. Such encounters could heat the surface and drive off volatiles. If the heating penetrated deeply, It could destroy any delicate organic structures. But depending on the specifics of the encounter, how close it came, how fast it moved, much of the interior could remain cold and unaffected. The core of 3I Atlas may never have been warmed significantly since its formation, meaning that whatever chemistry it started with could still be preserved. From a purely observational standpoint, all we can say is that 3I Atlas is an icy body from another star system, with detectable organic compounds in its coma and a structure capable of shielding its interior from radiation. These facts alone make it a natural candidate in discussions of panspermia, even if they do not prove anything about life. The debate is unlikely to be settled without a sample return mission to an interstellar object, a challenge far beyond our current capabilities, but one that is technically conceivable for the future. In the meantime, 3I Atlas serves as a reminder that our solar system is not isolated. Material is constantly entering and leaving, even if most of it is too small or faint to detect. Each detection is a rare glimpse of a process that has likely been shaping the chemistry of planets for as long as planetary systems have existed. Whether or not life has ever hitched a ride on such a journey, the potential for it to happen is woven into the physics of how these objects move. Considering the journey 3I Atlas has taken to reach us, its greatest scientific contribution may not lie in any single measurement, but in the broader context it offers about how planetary systems form and evolve. Even though we are separated from its place of origin by light years and millions of years of travel, its very existence carries information. Every property we can measure, its trajectory, its composition, its activity, feeds into a larger picture of the processes that govern planets, asteroids, and comets in systems far from our own. The first lesson comes from the fact that it exists at all. To send a body like 3I Atlas into interstellar space requires a sequence of events. In the early stages of a planetary system's history, when planets are forming and their orbits are still shifting, gravitational interactions can be intense. Giant planets in particular can scatter smaller bodies into elongated orbits that extend far beyond the main planetary region. Some of those bodies are nudged back inward over time, but others are accelerated to speeds exceeding the escape velocity of the system, breaking free entirely. The frequency and efficiency of this process depend on the number, size, and placement of giant planets, as well as the density of material in the system's outer regions. By studying the size, speed, and composition of interstellar objects that reach us, we can make inferences about how common and how violent these scattering events are in other systems. If most interstellar visitors turn out to be small, icy bodies with similar properties to long-period comets, that would suggest that outer regions rich in volatile material are a common feature of planetary systems. If we were to find instead that most are rocky or metallic, that would point to different architectures, perhaps with less emphasis on cold, icy reservoirs. The 3I Atlas seems to fit the cometry model, though with its own particular characteristics. Its low but measurable activity, its organic compounds, and its likely icy interior all support the idea that it formed far from its parent star, in a cold zone where ices could accumulate without being lost to evaporation. This mirrors the conditions in our own solar system's Kuiper belt and Oort cloud, lending weight to the idea that such structures are common. The more often we find interstellar comets with similar profiles, the more confident we can be that our system is not unusual in this respect. Its activity level is another instructive feature. While it does release gas and dust under solar heating, it does so at a rate lower than many long-period comets of similar size from our own system. This could be due to a thicker radiation-processed crust, a lower volatile content, or differences in the thermal properties of its surface materials. Any of these possibilities points to variations in the conditions of its formation and long-term storage. If its crust is thicker, that might indicate a longer exposure to cosmic rays in interstellar space, or perhaps a slower rotation that allowed localized heating and processing. If its volatile content is lower, That could mean it formed closer to its star than most Oort cloud comets do here. Even the subtle differences in dust composition hold clues. Preliminary measurements suggest that the dust grains in its coma are similar in size distribution to those in solar system comets, but small shifts in the details, more or less of certain minerals' different reflective properties, could be linked to the chemistry of its parent protoplanetary disk. These are the kinds of distinctions that, when collected across many examples, could reveal patterns in how disks evolve into mature planetary systems. The dynamics of its path through the galaxy also contribute to our understanding. Its moderate excess velocity and lack of extreme inclination relative to the galactic plane suggests that it is part of the general background population of interstellar debris, rather than an outlier from a recent violent event. This hints that the ejection of bodies like 3I Atlas is not rare, and that over the lifetime of the galaxy, a vast number of such objects have been set adrift, forming a low-density sea of planetesimals between the stars. In practical terms, that means our solar system is constantly moving through a diffuse cloud of interstellar debris, most of which is too small or faint to detect. The ones we do see are simply the largest and brightest that happen to cross our path. This has implications for impact risk. Though the odds are very low for a direct hit from such an object, it is not impossible, and for the steady accumulation of exotic dust on Earth and other planets over billions of years. The observation of 3 Atlas also highlights how much we can learn from even brief encounters. With each interstellar visitor, we refine our techniques for rapid detection, orbit determination, and characterization. These skills will be essential for the future, not just for basic science, but also for planetary defense and for the possibility of intercept missions. The more we understand the range of properties these objects can have, the better we can design instruments and strategies to study them in detail when opportunities arise. From a broader perspective, 3I Atlas reinforces the interconnectedness of planetary systems. Material does not remain forever bound to the star where it formed. The scattering and ejection of small bodies means that the building blocks of planets, and perhaps life, are constantly moving between systems, while the vastness of space ensures that any single object's journey is likely to be solitary. The cumulative effect over time could be significant. It is possible that some of the atoms now on Earth once formed part of a comet or asteroid in another star's planetary system, and that the same is true in reverse for material from our own system. In this sense, 3I Atlas is both a visitor and a messenger. It carries within it a record of a place we cannot see, shaped by processes that are familiar yet unique in their details. Every observation we make adds to a growing archive that will one day allow us to compare planetary systems not just by the planets we detect around distant stars, but by the debris those systems shed into the galaxy. This understanding naturally leads into questions about how many such objects are out there. What fraction of them might we detect in the coming decades, and what surprises they might hold? Questions that become all the more pressing when we realize how fleeting each opportunity is. The awareness that an object like 3I Atlas will not stay with us for long shapes almost every decision about how it is observed. From the moment of its detection, there is a countdown of sorts, not to a specific dramatic event, but to the gradual fading of opportunity. This is the reality of interstellar visitors. Their time in our observational reach is brief, and once they are gone for good. In the early days after discovery, the focus is on securing as much data as possible to pin down the orbit, because without that, predicting its position even weeks ahead becomes uncertain. The brightness changes, the sky background shifts, and the viewing geometry evolves quickly. Missing a few key observing windows can mean losing the ability to find it again, especially as it moves farther from the sun and its apparent motion slows. While the orbit of 3I Atlas was determined with enough precision to track it confidently for the rest of its passage, the principle remains: the clock is always ticking. For observers, There is a balance between depth and coverage. Longer exposures and higher resolution spectra can extract more detail, but they take time and often require specific conditions. Shorter, more frequent observations build a complete timeline of its behaviour, but may sacrifice some of that fine detail. Coordinated campaigns across observatories help resolve this trade-off, with different facilities contributing different kinds of data. Still, the pace is relentless. Any delay, whether due to weather, equipment issues, or scheduling conflicts, feels heavier when the object is already halfway through its inbound journey. As 3i Atlas passed perihelion and began its outbound arc, its apparent brightness began to drop. This was not just because it was moving farther from the Sun and Earth, but because the heating that drove its activity was declining. With less sunlight reaching its surface, the sublimation of ices slowed, the coma contracted, and the dust output decreased. Even though the solid nucleus remained, the faint haze of gas and dust around it, one of the primary sources of observational data, grew thinner. This fading happened gradually, but with enough regularity that astronomers could predict when certain measurements would become impractical. Some wavelengths became harder to work with sooner than others. Spectral lines from certain volatiles weakened until they were lost in the noise. Photometric measurements had to contend with the fact that the brightness of the coma was approaching the level of the background stars, making it more challenging to separate the signal from the noise. Instruments optimized for faint object work could extend the observational window, but even they had limits. By the time it moved far enough away that only the largest telescopes could detect it, 3i Atlas was already a far dimmer target than it had been just weeks earlier. The visual change in its appearance was subtle to the eye but unmistakable in the data. A sharper point of light, less surrounded by diffuse glow, and with less variation in brightness over time. The tail, faint to begin with, became nearly undetectable, reduced to a whisper of light in long exposures. These changes are a normal part of a comet's life cycle within the solar system, but for an interstellar visitor, the knowledge that we will never get another chance makes them feel different. Every faintening image is a reminder that the encounter is ending. There is no hope of catching it again decades or centuries later, as we might with a long-period comet from our own Oort cloud. Once it crosses the boundary of our observational reach, it will simply continue into the dark, becoming just another untraceable point of debris among billions in the galaxy. For scientists, this urgency shapes how they allocate resources. Observations that require the highest sensitivity are prioritized while the object is still bright enough. Measurements that can be made even at low brightness levels are saved for later, when other techniques have become impossible. This triage ensures that the most perishable data, like weak spectral lines from uncommon volatiles, are not lost to the fading light. Even so, there is an emotional component to this process. Many of the people observing 3i Atlas may never have another chance to study an interstellar object firsthand. While the odds of detecting more have improved with modern surveys, the rarity of these events means that each one feels singular. The object itself does not slow down, wait, or linger. It simply follows its trajectory, indifferent to our curiosity. The vanishing act is not dramatic, not a sudden disappearance, but a slow retreat into invisibility. As the brightness declines past certain thresholds, the number of observatories capable of continuing the work shrinks. Smaller telescopes drop out first, unable to distinguish the target from the sky background. Even for the largest facilities, the object eventually becomes too faint for useful measurements. At that point, the decision to end observation is not taken lightly, but the diminishing returns make it inevitable. Resources are finite, and other targets compete for time. The final confirmed observations of an interstellar visitor often come from a handful of dedicated teams, using the most sensitive instruments available, pushing the limits of exposure time and data processing to squeeze out the last measurable photons. For 3i Atlas, these last images and spectra will be archived alongside the earliest ones, forming the complete record of its time in our solar system. The arc from first detection to final sighting tells a story of a fleeting encounter, captured in data but gone in reality. After that, The only way to follow it is through mathematics. The orbital parameters allow us to predict where it will be for centuries, even millennia, though it will be far too faint to observe. It will pass through regions of space empty to our eyes, its path gently bent by the gravity of the stars it passes, until some distant epoch when it drifts into another planetary system. There, the process could begin again, with another civilization pointing instruments toward a faint moving point of light and wondering where it came from. Knowing this does not lessen the value of the time we have with such objects. It increases it. Each observation is unique not just because the object itself is rare, but because the circumstances of its visit can never be replicated. The alignment of orbits, the state of our technology, the readiness of our survey networks, all combine to make a specific window of opportunity. Miss it, and it is gone forever. From here, the natural question becomes how we might be better prepared for the next time, not only to make the most of its brief visibility, but perhaps to do something we could never do with 3i Atlas, meet an interstellar visitor up close. The gradual fading of 3i Atlas brings with it an inevitable sense of unfinished business. We have learned much from a distance, yet the most tantalizing answers lie locked within the object itself, beyond the reach of our telescopes. The idea of sending a spacecraft to intercept it is as compelling as it is impractical under current circumstances. The speeds involved are beyond anything our fastest missions have achieved, and the timeline from discovery to closest approach is far too short for us to design, build, and launch an interceptor from scratch. By the time we realize what we are looking at, it is already moving past us, bound for the deep beyond. This limitation is not unique to 3i Atlas. It applied to Oumuamua before it and Borisov after it, and will apply to most interstellar visitors unless we change the way we prepare for them. The core of the problem is that these objects arrive with no warning, from random directions at high velocities and on non-repeating paths. Unlike comets and asteroids native to the solar system, there is no advance prediction of their arrival. We are limited to reacting to a discovery made by wide-field survey telescopes scanning the sky each night, and in many cases that discovery happens only weeks or months before closest approach. To chase something like 3i Atlas, a spacecraft would need to launch almost immediately upon detection or already be in space, waiting for the opportunity. The first approach, rapid development and launch, demands an unprecedented level of readiness and flexibility in mission design. The second, pre-positioned spacecraft, requires a long-term commitment to maintaining and operating probes that may wait years, even decades, before having a target. Both approaches come with substantial costs and technological challenges, but neither is impossible in principle. One proposal that has gained attention is to design a ready-to-go interstellar interceptor, parked in a solar orbit where it can be launched toward a newly discovered object with minimal delay. Such a mission would not require knowing the exact target in advance. It would simply be capable of adjusting its trajectory once the opportunity arises. The key would be high delta-V capability, a measure of how much a spacecraft can change its velocity to match or at least approach the high speed of an incoming object. Technologies like advanced chemical propulsion, solar electric propulsion, or even solar sails have all been suggested as ways to achieve the necessary performance. Solar sails, in particular, offer an intriguing possibility. By harnessing the pressure of sunlight, a large lightweight reflective sail could gradually accelerate a probe to very high speeds without using fuel. If such a craft were deployed years in advance, it might be able to match the trajectory of an interstellar object given sufficient lead time. The trade-off is that sails require large surface areas and precise control, and they work best when starting close to the sun, where the light pressure is strongest. Maneuvering them onto a rendezvous path would be complex but potentially achievable with careful planning. Another idea involves using gravity assist from planets, or even the sun itself to gain speed. A spacecraft could be sent on a path that takes it very close to the sun, where a precisely timed maneuver could dramatically increase its velocity. This Oberth maneuver is one of the most efficient ways to achieve high speeds, but it requires the spacecraft to endure intense heat and radiation. Advances in thermal shielding, like those tested on solar probes, could make such missions possible in the coming decades. Even with these techniques, matching the exact speed and trajectory of something like 3i Atlas is daunting. Rendezvous, the ability to arrive at the object and remain close enough for detailed study, is far more challenging than a simple flyby. A flyby mission could still return valuable data, much as past missions have done for comets and asteroids within our solar system, but the encounter time would be short. Instruments would have only minutes or hours to collect high-resolution images, spectra, and other measurements before the object raced away. The dream scenario for many researchers is a sample return mission, bringing material from an interstellar object back to Earth for direct analysis. Such a mission would be technologically complex and require a long-term commitment, but the rewards would be unmatched. Even a few grams of material would give us a laboratory view of matter from another star system, preserving details of its composition, structure, and isotopic ratios that are impossible to obtain remotely. The problem is that returning samples at interstellar speeds would require slowing the spacecraft dramatically, which adds another layer of propulsion challenges. For now, the best path forward is likely to be a combination of improved detection capabilities and flexible mission architectures. The sooner we can spot an interstellar visitor on its inbound leg, the more options we have for interception. Upcoming survey telescopes, like the Vera C. Rubin Observatory, with its large synoptic survey telescope, will greatly increase our ability to detect faint, fast-moving objects earlier in their approach. This could add weeks or even months to the lead time, which might be just enough to make a well-prepared mission feasible. There is also the possibility of piggybacking on missions designed for other purposes. A spacecraft sent to study comets or asteroids within the solar system could be designed with the flexibility to retarget in the event of an interstellar discovery. While this approach would not provide the perfect interception profile, it might still yield close-up data that we cannot obtain from Earth. The reality is that most interstellar visitors we detect in the near future will still pass us by unchallenged. But each detection gives us a better understanding of the range of possible velocities, approach angles, and brightness levels we might expect. This in turn feeds into mission design studies, which can simulate a wide variety of encounter scenarios and refine the strategies for capturing them. The more prepared we are, the more likely it becomes that one day, perhaps not long from now, we will be able to meet such a traveller in space, not just watch it from afar. Until then, objects like 3i Atlas remain, in a practical sense, unreachable. We watch them enter our solar system, pass near the Sun, and leave again, tracing arcs we cannot follow. Yet even at a distance they offer a wealth of information, enough to reshape our understanding of planetary systems, the galaxy's inventory of small bodies, and the movement of material between stars. They remind us of the limits of our reach, but also of how far that reach has already grown. Once 3i Atlas had passed its closest point to the Sun and begun its steady retreat, it joined the far longer list of objects that have slipped into the dark again. But unlike comets native to our solar system, its outbound journey is permanent. There is no wide arc that will carry it back centuries from now, no loop through the Oort cloud to bring it within reach again. Instead, it is heading outward along a path that will eventually take it beyond the gravitational influence of the Sun entirely, into the same interstellar medium from which it came. In a sense, it is now just another piece of the galaxy's debris stream, moving between the gravitational domains of stars. Each such object is like a sealed parcel, dispatched at some point in the past from a planetary system, carrying whatever materials it formed with, whatever changes have been imprinted on it by cosmic rays, impacts, and heating events, and whatever record its internal chemistry still holds. We may never open this particular parcel, but others like it are certainly out there, and some fraction will cross our path again. The analogy to a cosmic mail system is difficult to resist. Planetary systems are not isolated islands. They are more like nodes in a slow, sprawling network, constantly sending and occasionally receiving physical material. Ejection events act as the mailing process, flinging bodies into interstellar space. Travel through the galaxy is the delivery route, a journey that might take millions or even billions of years, and encounters with other stars are the deliveries, though in most cases the recipient never notices. A star's planets may remain untouched, while the visiting object sails through its outskirts without any close approaches. But on rare occasions, one of these travellers will find itself drawn toward a star in just the right way to pass close to a planet or moon. 3i Atlas is an example of such a delivery, even if our interception was only observational. Its trajectory through our system was purely a matter of celestial mechanics, the sun's gravity bending its path into a curve that took it inside the orbit of Earth and then back outward again. But for us, this was more than just a piece of galactic driftwood passing by. It was a messenger from a place we have never seen, carrying evidence of the processes that shaped it and the system it came from. This constant exchange of material between stars has implications for everything from planetary formation theory to the possible spread of organic chemistry. While most of the galaxy's small bodies will never encounter another planetary system closely enough to be significantly altered, the sheer number of them makes occasional interactions inevitable. And when those interactions happen, the material exchanged can be chemically rich. Even if the likelihood of such material contributing to the origin of life elsewhere is small, the possibility remains, supported by the fact that we already see complex organic molecules forming in interstellar clouds without any planetary influence at all. For most of its journey, an object like 3i Atlas is in a state of extreme stability and isolation. It is not orbiting anything. It is simply coasting under the combined gravitational influence of the galaxy as a whole, with small perturbations from passing stars and molecular clouds. These influences are usually too weak to make major changes in a single pass, but over long timescales, they can alter the object's direction enough to set up a future encounter with another star. The result is a kind of slow-motion mixing process, where the galaxy's stock of small bodies is continually redistributed. From the perspective of our solar system, each interstellar visitor we detect is a sample from this shared inventory. Just as meteorites from Mars tell us about that planet's composition without requiring a dedicated mission, an interstellar object offers a direct look at material from a star we may never visit. The difference is that meteorites are physically here, in our laboratories, while an interstellar object like 3i Atlas remains far away, forcing us to do all our work remotely. That makes every measurement more challenging, but also more valuable, because we know that our window is short and our next opportunity is unpredictable. Thinking about the cosmic mail system also raises questions about the reverse process, how often we send material outward that will one day pass through another system. Our own solar system has ejected countless icy bodies over its history, most during its early formative period. Each of those bodies is now somewhere in the galaxy, perhaps still in pristine condition if it has avoided close encounters, perhaps altered by the same radiation and impacts that affect all interstellar travellers. In the vastness of space, most will never come close to another planet, but over enough time, some of them will. For the recipient, those will be just as mysterious as 3i Atlas is to us, an unfamiliar object on a hyperbolic path carrying the chemistry of a star they have never seen. There is no central sorting facility for this cosmic mail. The process is random and continuous, governed only by the mechanics of motion and the occasional gravitational coincidence. Yet over billions of years, the amount of material exchanged must be enormous, even if each individual delivery is rare. This has implications not just for the spread of molecules, but for the slow blending of solid matter across the galaxy. Atoms and minerals forged in one star system may find their way into planets in another, creating a kind of galactic inheritance that links distant worlds in subtle ways. The outbound path of 3I Atlas is simply the next leg of its delivery route. After leaving the solar system, it will travel for millions of years before another close encounter with a star alters its course. In the meantime, it will remain silent and inert, preserving whatever it carries until the next opportunity arises. That opportunity may be as uneventful as a pass through the outer reaches of a planetary system, or as dramatic as a plunge into the atmosphere of a young planet, delivering dust and ice to its surface. In either case, the journey will continue, part of a process that has been shaping the galaxy since long before our sun formed. For us, 3I Atlas's role in this system is a reminder that the galaxy is not a static backdrop, but a place of slow, constant movement. Stars orbit the galactic center. Molecular clouds drift and form new generations of stars, and countless small bodies pass between systems, carrying the signatures of their origins. Each one is a potential piece of a much larger story, a record of events in another corner of the galaxy, delivered to us not by intention, but by the same physics that governs the motion of everything in space. From this perspective, the object's departure is not an ending so much as a change of address. It is leaving our region of space, but its journey continues, and in time it may become a delivery for another set of observers in a place we cannot yet imagine. The thought that our encounter with it is just one chapter in a much longer narrative is part of what makes these fleeting visits so compelling. The thought that 3I Atlas is simply the latest in a chain of countless interstellar travellers invites a deeper look at the age of these objects. While we often focus on their recent history, the path they take into and out of our solar system, the reality is that most of their journey took place long before our sun even existed. These are ancient messengers in the truest sense, carrying within them a record of conditions from an earlier time in the galaxy's history. It is difficult to pin down exactly when an object like 3I Atlas formed. Its age is measured not in millions, but in billions of years. If it originated in a planetary system much older than ours, it could have been ejected into interstellar space when the Milky Way was a different place entirely. When the distribution of stars, gas and dust was shaped by past generations of supernovae and the slow dance of spiral arms. Even if it came from a system similar in age to our own, the time since its ejection may still stretch far beyond the entire history of human civilization. The composition of such an object is like a sealed archive. The ices, minerals and organic molecules locked inside are the direct products of its parent system's formation environment. Ratios of certain isotopes can reveal the abundance of elements at the time and place it formed. The specific mix of volatile compounds can hint at the temperature and radiation conditions of its natal disk. These details are the sort of clues planetary scientists seek when reconstructing the history of our own solar system, and interstellar objects offer the chance to apply those same techniques to material from elsewhere. But in interstellar space, time leaves its own marks. High-energy cosmic rays gradually alter the chemistry of surface layers, breaking molecular bonds and creating new, more complex compounds. Impacts with micrometeoroids chip away at the surface, while ultraviolet light from nearby stars slowly erodes unprotected ices. Over millions of years, these processes form a kind of weathered crust, a protective layer that shields the interior from further alteration. This crust is a record in itself, marking the length of exposure to interstellar space and the balance between damage and preservation. For 3I Atlas, the thickness and nature of this crust can only be inferred from indirect evidence. Its relatively subdued activity compared to many solar system comets suggests that its surface may be more processed, with fewer exposed volatile-rich areas. That would be consistent with a long journey through interstellar space, where active ices are buried beneath layers of refractory material. If so, the interior could be remarkably well preserved, holding chemistry from its origin point with minimal changes. The notion of ancient messengers also extends to the possibility that the conditions which created objects like 3I Atlas were more common in the early galaxy. Planetary systems may eject more material in their youth, during the chaotic phase when planets are still shifting into stable orbits. If the galaxy's average rate of such ejections was higher in the distant past, then the population of interstellar objects we see today may include a disproportionately large number of older ones. In that case, 3i Atlas could be carrying not just the story of its own system, but a snapshot of an era when the Milky Way was younger, denser, and perhaps more dynamic in terms of planetary interactions. Thinking about this in geological terms, these objects are the bedrock samples of galactic history. Unlike light from distant stars, which tells us only about their outer layers, at the moment we observe them, an interstellar object is a piece of physical material we could, in principle, touch and analyse directly. In its structure, its chemistry, and even its imperfections, it holds a record of processes that occurred far away and long ago. It is as though a fragment of a lost continent had drifted across an ocean to land at our feet, offering a tangible link to a place we will never see. It is also worth noting that these messengers are not just records of planetary systems, they are records of the space between them. Their time in interstellar space exposes them to a unique set of conditions: a sparse but constant flux of particles, the weak but unceasing tug of the galactic gravitational field, and occasional encounters with shock waves from supernova remnants or the edges of giant molecular clouds. Each of these events can leave subtle traces in the object's structure or chemistry, traces that could be detected in a laboratory sample. From our current vantage point, we can only guess at these histories. Without the ability to intercept and study such an object up close, much of its story remains hidden. But even remote measurements can offer hints. The colours we measure in reflected sunlight, the composition of the gases released as it warms, and the way its brightness changes with distance all provide pieces of the puzzle. Together, these clues can suggest whether we are looking at a body that has spent eons in deep space, or one that was ejected more recently. The fact that 3i Atlas is the third confirmed interstellar object we have detected means our sample size is still extremely small. It is too soon to say whether its properties are typical or unusual. But that small number also reinforces how rare and valuable these encounters are. Each one we find is an ancient messenger arriving at a random point in its journey, and each carries a story from a different place and time in the galaxy. If we could assemble enough of these stories, we might begin to see patterns, similarities in composition that point to common formation environments, or differences that reflect the diversity of planetary systems across the Milky Way. For now, though, the story of each messenger remains largely individual, shaped by its own origin and history. And as with any message, the value lies not just in the content, but in the realization that it came from far away, and that its journey to us was shaped by forces and events beyond our control or even our awareness. This atlas is one such message, and while we cannot read it in full, we can at least recognize its significance. Behind the measurements, orbital calculations, and scientific papers, there is the reality that every discovery like 3i Atlas begins with a person, or more often a team of people, looking at data and noticing something that does not quite fit. For all the automation and processing power in modern astronomy, there is still a moment when a human being first sees the evidence of something new and understands what it might mean. That moment carries with it a mix of curiosity, responsibility, and excitement that is hard to replicate in any other field. In the case of 3i Atlas, the initial detection came from one of the automated survey systems scanning the sky each night. The raw data were processed by algorithms designed to spot moving points of light that could be asteroids or comets. Most of what the system flags turns out to be known objects or new additions to familiar categories. But every so often, a track appears that does not match the expected motions of anything in the catalogue. It was in one of those moments that 3i Atlas first appeared, a faint dot moving just differently enough to raise questions. Once flagged, the data go to astronomers who confirm the detection and begin calculating its orbit. In the early stages, those calculations are uncertain. It takes multiple nights of observations to refine the numbers enough to reveal whether the path is elliptical, indicating an object bound to the sun, or hyperbolic, which would mean it is passing through from outside the solar system. The realization that a track is hyperbolic is a rare one, and when it happens, it changes the nature of the work. Suddenly, what might have been another entry in the endless catalogue of small solar system bodies becomes a potential first-hand look at something from another star. The people involved know how rare this is. There are astronomers who have spent entire careers without ever encountering a confirmed interstellar object. For the teams working on survey data, it is not just a scientific achievement but a professional milestone, one of those moments they will always remember. There is a sense of urgency too, because the discovery is only the first step. The next priority is to alert the broader community so that telescopes around the world can begin observations while the object is still bright and accessible. That process requires rapid communication and coordination across time zones and institutions. In those first days after discovery, there is often very little sleep for the scientists involved. Emails and messages arrive at all hours as new data come in. Observers in different countries take turns tracking the object as the Earth rotates, passing the baton so that coverage is as continuous as possible. Instruments are retasked, observing schedules reshuffled, and proposals for telescope time submitted on short notice. All of this happens against the clock because every day that passes changes the geometry of the observation and the strength of the signal. There is also a personal side to this work that does not always make it into the formal reports. For the people staring at the incoming data, there is the quiet thrill of knowing that they are among the very first human beings to see this particular object. It has been travelling for millions of years, and yet it is only in this short window that it comes close enough to be noticed. That awareness adds a weight to each image and measurement, a sense that these are not just numbers but pieces of a fleeting event. In interviews and informal conversations, some astronomers have compared it to meeting a traveller from far away who will never return. There is a certain humility in knowing that the visitor's journey is vastly larger in scope than our ability to follow it, and that all we can do is learn what we can during the brief time it is with us. That perspective can make the long hours and logistical challenges feel not just worthwhile but essential. As the days turn into weeks, the rhythm changes. The initial rush of confirming the orbit and securing early observations gives way to a more deliberate effort to collect as much high-quality data as possible before the object fades. Teams specialise in different aspects. Some focus on photometry to track changes in brightness, others on spectroscopy to identify chemical signatures, and still others on astrometry to refine the trajectory. The work becomes less frantic but no less intense, as every set of observations adds detail to the emerging picture of what 3i Atlas is. There are moments of frustration too. Bad weather can wipe out carefully planned observation windows. Technical issues can delay the collection of crucial spectra. Sometimes the object itself surprises observers, behaving differently than predicted, forcing changes in strategy. All of this is part of the process, and it adds to the sense that each data point is hard-won. For many of the people involved, there is also a public dimension to the discovery. Once the news spreads beyond the scientific community, they become the ones answering questions from journalists, students, and curious members of the public. Explaining the significance of an interstellar object is not difficult. Most people intuitively understand the rarity and intrigue of something from another star, but doing so in a way that is accurate without being overly technical is a skill in itself. These conversations are part of how the discovery moves from the realm of specialists into the broader human story of exploration. That broader story matters because it connects the work of scientists to the curiosity that has driven human beings to look at the night sky for millennia. The instruments are more advanced now, the data processing faster, the calculations more precise, but the core motivation is the same: to understand what is out there and what it means for us. In the case of 3i Atlas, the answer to that question is still unfolding. But the human side of the discovery, the people who first noticed it, the ones who tracked it, the ones who coordinated observations around the world, is already part of its history. And when the object finally fades beyond reach, that history remains. The data will be stored in archives, the papers published, the orbital parameters preserved for anyone who wants to know where it will be centuries from now. But for the people who were there at the beginning, there will also be the memory of those first images, the late nights, and the knowledge that for a brief moment they were connected to a piece of the galaxy that had travelled unimaginable distances to cross our sky. When the last images of 3I Atlas were logged and its light was too faint for even the largest telescopes to track, what remained was not just the data, but the awareness of scale. The entire event, from the moment it first appeared on survey images to its final measurable position, was just a brief crossing in a space that is almost unimaginably large. In the span of its journey, our encounter with it is the smallest fraction of time, less than a blink, less than the pause between two heartbeats. It is a reminder that what we saw was not the whole of its existence, but only one point along a vast unbroken path. That path is part of a galactic ocean, an enormous three-dimensional expanse in which stars, gas clouds, dust and small bodies are constantly in motion. Our solar system is like a single vessel adrift in this ocean, surrounded by billions of others, each with its own cargo of planets, moons, asteroids, comets, and fragments like 3I Atlas. The scale is not something our minds can fully grasp, but its consequences are visible in the rare moments when two paths cross. The fact that 3I Atlas reached us at all, travelling on exactly the right trajectory to pass close enough for us to detect, speaks to the sheer number of such travellers that must be moving through this ocean at any given time. And yet, most go unseen. Our detection capabilities, advanced as they are compared to the past, still cover only a small slice of the sky each night, and only for objects above a certain brightness. Fainter, smaller visitors likely pass through regularly without notice, their speeds and distances keeping them hidden in the background. It is possible that the solar system has been crossed by many such bodies in human history without any record, simply because the instruments and methods to find them did not yet exist. Even today, we are only sampling the most visible portion of this hidden traffic. This is why each confirmed interstellar object carries more weight than its size would suggest. It is not just an isolated rock or ball of ice. It is a detectable example of a much larger, mostly invisible population. Astronomers can use the number of discoveries, combined with the volume of space surveyed and the sensitivity of the instruments, to estimate how many such objects might be moving through the inner solar system each year. The numbers suggest that they are not rare in absolute terms, but rare in terms of our ability to notice them. The comparison to a drop in the ocean is tempting but incomplete. In a literal ocean, a drop is not distinct. It blends immediately into the whole. In the galactic ocean, each object remains an individual, carrying its own history, composition, and structure, even as it moves among countless others. If we could somehow map every small body in the galaxy, we would see an intricate shifting pattern of trajectories, like currents within a vast sea, shaped by the gravitational pull of stars and the occasional disturbances of passing systems. Our place within that pattern is not fixed. The Sun orbits the centre of the Milky Way, carrying its planets along at an average speed of over 800,000 kilometers per hour relative to the galaxy. Over the course of hundreds of millions of years, it passes through different regions, spiral arms, interarm spaces, areas denser or sparser in stars and clouds. Each of these environments may have a different density of interstellar debris, so the rate at which we encounter objects like 3I Atlas could change over geological timescales. In some epochs, the traffic might be heavier. In others, it might be so sparse that no significant visitor comes close for hundreds of thousands of years. On human timescales, though, the ocean feels calm. The arrival of an interstellar object is rare enough to be an event, yet common enough that we now expect to see more of them in the coming decades as survey systems improve. Each detection is both a triumph of technology and a sign of how much remains unseen. In the case of 3i Atlas, its detection was a success, but also a reminder that if its size or brightness had been just a little less, we might have missed it entirely. That possibility, that many are simply passing unnoticed, has implications for our understanding of the galaxy's structure and history. If we are only seeing the brightest and largest examples, we are likely underestimating the total population. Smaller, darker objects could be far more numerous, representing the bulk of the material exchange between systems. If so, the galactic ocean is richer and more active than our current observations can confirm. This uncertainty shapes the way astronomers plan for the future. Expanding detection networks, deploying space-based telescopes to avoid the limitations of Earth's atmosphere, and developing automated systems that can process enormous amounts of sky survey data are all part of an effort to better map this ocean. The more we can see, the better we can understand the scale and nature of the traffic within it. That knowledge in turn feeds into everything from theories of planetary formation to models of how organic compounds might spread across the galaxy. When we look at 3i Atlas through this lens, it becomes more than a solitary traveller. It becomes a data point in a vast statistical picture. Its properties, combined with those of Oumuamua, Borisov, and any future interstellar objects, will slowly fill in that picture, giving us a clearer sense of how the galaxy moves and mixes its small-scale matter. Each new arrival will refine the map, perhaps revealing clusters of similar objects that originated in related systems, or highlighting outliers that point to unusual processes at work. This is the quiet power of treating each detection as a piece of a larger whole. In the moment, it is easy to focus on the uniqueness of the visitor, its speed, its composition, its sudden appearance. But over time, the patterns that emerge from multiple discoveries will tell us more than any single object can. The drop becomes part of a current, the current part of a flow, and the flow part of the ocean itself. For now, our understanding of that ocean is limited, but growing. Each time an object like 3i Atlas passes through, we glimpse a little more of its depth and complexity. And while we may never see the entire map, each encounter adds to our awareness that we're not isolated, but part of a constant, if subtle, exchange of material on a galactic scale. Thinking of 3i Atlas as one point in a much larger ongoing exchange of material naturally leads to the question of where we go from here. Each detection improves our picture, but it also raises new questions. If the galaxy is filled with travellers like this, some of them perhaps passing close to us every year, then the challenge is no longer whether they exist, it is how we can study them better, sooner and more deeply. The work we have done so far feels like the opening chapters of a story that could eventually stretch across centuries, with each generation building on the encounters of the last. One of the most immediate developments is the expansion of our detection capabilities. Ground-based surveys are growing more powerful every year, with larger mirrors, more sensitive detectors, and wider fields of view. The Vera C. Rubin Observatory, once it begins full operations, will transform our ability to spot fast-moving, faint objects weeks or months earlier than before. That added time could make the difference between a brief glimpse and a coordinated campaign that captures a complete picture of an interstellar visitor's behaviour. Space-based telescopes will add another layer to this effort. Freed from the distortions and limitations of Earth's atmosphere, they can detect fainter objects against the dark background of space, observe across wavelengths blocked by air, and operate continuously without the interruptions of day and weather. The possibility of dedicated satellites scanning for interstellar bodies is increasingly discussed in both scientific and engineering circles. If such missions are launched, they could fill the gaps left by ground-based networks, creating an almost unbroken watch on the sky. Improved detection is only part of what comes next. The deeper challenge is how to respond quickly enough to turn early sightings into detailed observations. That means refining not just the technology, but the infrastructure of coordination, how observatories share data, how time is reallocated for urgent targets, and how different kinds of instruments are brought to bear on a single object in a short time. The process already exists in a loose form for comets and asteroids, but interstellar objects add a level of urgency that demands more streamlined, flexible systems. Beyond remote observations lies the dream of direct exploration. The concept of a rapid response interstellar interceptor is no longer just an abstract idea. It is the subject of real mission studies. Engineers are exploring what kind of propulsion, navigation, and onboard instrumentation would be needed to make even a fast flyby possible. The designs vary, but they all face the same constraints: high speed, short notice, and the need for a payload capable of returning meaningful data in a matter of minutes or hours during the encounter. For many researchers, the ultimate goal is not just a flyby but a rendezvous, a mission that can slow enough to stay near the object for days or weeks, mapping its surface, sampling its dust, and perhaps even deploying small landers. This is a much harder problem, requiring far greater velocity changes than a flyby. It may demand propulsion technologies that are still in early stages of development, but the payoff would be immense: a detailed, close-up study of material from another star system, unaltered by atmospheric entry or the long journey through space to reach us. And then there is the most ambitious possibility of all: a sample return. Bringing back material from an interstellar object would allow analysis with the full range of laboratory tools, far beyond what any spacecraft can carry. The amount of information we could extract from even a few grams of such material would transform our understanding of planetary formation, chemical evolution, and the diversity of matter in the galaxy. But such a mission would require not only extraordinary engineering, but also extraordinary foresight. The window for launch would be short, the speed requirements extreme, and the challenges of returning the sample without contamination formidable. None of these goals will be achieved by a single nation or space agency. The nature of the challenge, short notice, rare opportunities, and the need for resources from across the globe makes international cooperation almost inevitable. The scientific community has already seen this with comets and asteroids, where data from multiple countries are combined into a shared record. For interstellar objects, the need will be even more pressing, because no single observatory network or space program can guarantee complete coverage. Alongside the technical and logistical work, there will also be a shift in mindset. Interstellar visitors are no longer hypothetical. They are a recurring part of our observational reality. This means they can be incorporated into broader scientific planning, given space in budgets, and considered in the design of future telescopes and missions. The expectation will grow that when the next one appears, we will be ready, not scrambling from a standing start, but executing a plan refined through simulations and past experience. Public interest will almost certainly follow this progression. The story of a visitor from another star resonates far beyond astronomy. It speaks to curiosity, to exploration, to the sense that we are part of something larger and more dynamic than our immediate surroundings. Each detection will be a chance to engage people with the science and the wonder of the galaxy. That engagement matters, because it is public interest that often sustains the political and financial support needed for ambitious projects. Looking further ahead, it is possible to imagine a time when missions to interstellar objects are routine, much as planetary flybys and comet encounters are now. Such missions could form part of a broader exploration program that treats the solar system not as an isolated bubble, but as one node in a galactic network. Just as ocean voyages in the past expanded human understanding of our planet's geography, journeys to and from interstellar visitors could expand our understanding of the galaxy's geography, not in the sense of fixed maps, but in the sense of knowing how material moves, mixes, and changes over time. For now, though, the next steps are more immediate and focused. Build better eyes to find the travellers sooner, develop the tools to meet them on their way, and prepare to learn as much as possible from each fleeting encounter. 3i Atlas has shown that the opportunity is real, the benefits tangible, and the sense of connection profound. The next visitor may be larger, closer, brighter, or simply different in a way that changes our understanding entirely. Even as the plans for what might come next take shape, there is the quiet knowledge that 3i Atlas itself is already gone. The images we have, the spectra, the numbers, they are the only direct traces we will ever have of its visit. Out there, somewhere beyond the reach of our largest telescopes, it continues on the same unbroken path it followed into our solar system, slipping back into the deep background from which it emerged. It is not lost exactly. Its position and velocity are known well enough that we can project its future course far ahead. But for practical purposes, it has passed beyond our ability to watch, leaving us with only the record of its brief appearance. There is something in that quiet departure that lingers in the mind. The way it entered our awareness suddenly, then faded without pause, feels almost like a meeting with someone who doesn't slow down to talk, but still leaves you with the certainty that the encounter mattered. It is tempting to think of the object as waving goodbye, though of course no such gesture exists. The wave is only in our minds, a way of giving shape to the mix of curiosity and distance that defines our relationship with it. In reality, there is no pause in its motion, no backward glance. Interstellar objects do not linger out of sentiment. They move according to the same physics that governs everything else in space. Its speed now ensures that it will never return, not in any time scale relevant to our species or our planet. The sun's gravity will not pull it back, and the planets it passed have no hold on it. In that sense, it has already been free for millions of years, long before we knew it existed. Our encounter did not capture it, and its departure is no escape, just the continuation of what it was always doing. Still, it is hard not to assign meaning to the fact that, for a short while, our paths overlapped. It came from somewhere far away, crossed our home, and went on towards somewhere else entirely. That path is unique, shaped by a chain of events stretching back to its formation, perhaps in the disk of a young star, perhaps in a system that has since changed beyond recognition. Each part of its surface, each molecule in its ices, is part of that history, and for a moment those details were within reach of our instruments and our attention. When astronomers talk about missing it already, they are not speaking of the object as if it were a friend, but of the work that came with its presence. The observations gave each day a focus, each night a goal, and the end of that work leaves a quiet gap. Data analysis continues for months or years afterward, of course, but there is no longer a need to check the weather over observatories, no urgent messages about changing brightness, no coordination calls to fit in one more spectrographic run before dawn. The tempo of the work slows, and in that slowing, there is space to think about the meaning of the encounter itself. For the broader public, the story fades more quickly. A few headlines, a scattering of news segments, maybe a handful of follow-up articles when major results are published. The visitor is remembered in passing, if at all, and then replaced in attention by something else. Another discovery, another event. That is natural. The galaxy is not on a schedule that aligns with our daily news cycles, and most people do not live in the rhythm of telescopes and observation windows. But for those who tracked it from the moment it appeared, it is different. They know exactly where in the sky it was on any given night, how fast it was moving, and how bright it became at its peak. That knowledge is not replaced. It simply becomes part of their own mental record of the sky. The idea of waving goodbye, even metaphorically, carries with it a recognition of time's flow. The same Earth that rotated under the sky during its visit keeps moving, seasons changing, the sun's position shifting, constellations rising and setting. The point in space where we first saw 3i Atlas is now empty, and so is the point where we last measured it. The memory of those points is fixed, but the reality has moved on. The galaxy does not hold still for us to revisit moments. It moves on its own terms, and we move with it. there is also the thought that this goodbye is one of many. We have already had to let go of Oumuamua and Borisov, and in the years ahead, there will be others. Each will arrive suddenly, stay briefly, and then go, taking with it the possibility of more direct knowledge. The pattern will repeat, and with each one we will learn to say goodbye a little more easily, not because it means less, but because we will understand better what these encounters are, intersections of paths that cannot be made to linger. And yet, there is a certain optimism in this pattern. The fact that we have now seen several interstellar visitors in such a short span of time suggests that we will see many more. Each new detection is an opportunity, and even if none stay, the accumulation of brief visits will build a deeper, broader picture of the galaxy's small bodies. In that sense, waving goodbye is not a closing gesture, but part of an ongoing exchange. We see them, they pass, and we keep watching, knowing that the next one is somewhere out there already on its way. For 3i Atlas, the road ahead is long and unbroken, a course that will take it into regions of space where no sunlight will touch it for centuries at a time. It will pass within range of other stars eventually, perhaps skimming the edges of their planetary systems, perhaps altering course slightly from their pull. It may be noticed again by another civilization, or it may drift on unnoticed, just one more faint, cold traveller in the galactic background. Whether it is ever seen again or not, its journey will continue indifferent to our brief moment of awareness. Here, on our small planet, we have the luxury of thinking about it in human terms, of framing its passage as a visit and its departure as a farewell. The truth is more neutral, but that does not make the encounter less meaningful. The meaning comes from the act of looking, of recognizing that what passed through our sky was not part of our solar system, but part of something much larger, and that we were here to witness it. And so, the goodbye is both simple and expansive. It is an acknowledgement of distance, of motion, of the fact that we are part of a galaxy that will not slow down for us, yet still offers us these moments of connection. It is a quiet reminder to keep looking outward, to be ready for the next time, and to remember that even in the vastness, paths can cross in ways that leave an imprint. 3 Atlas is gone, but it was here and we saw it. That is enough to carry forward until the next traveller appears on the horizon. And as we leave 3i Atlas to its journey, the night sky above us is still full of quiet motion. Somewhere out there, in the vast sweep between the stars, the next traveller is already on its way, following a path that will one day cross ours. We may not know its name yet, or when it will appear, but we will be here, looking up, ready to notice. If you've enjoyed drifting through this story with me tonight, feel free to subscribe, leave a comment, or share this with someone else who finds comfort in the slow unfolding of science. It helps keep this space alive, and it lets me keep making these long, quiet explorations for you. Until next time, may your nights be calm, your curiosity steady, and your dreams wide enough to hold the whole sky.